Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So my dear students, quickly let me know if all of you can see me, if I am perfectly audible to everyone. Good evening everyone, good evening and welcome back. So let me know in the chats quickly if all of you can hear me, if I'm perfectly audible, visible to everyone. Welcome back people, welcome back. So all set, everything is perfect? Yeah? All right, wonderful. So dear students, just let me know once in the chats whether you watched the first session of Chemical Kinetics or not. Just let me know once in the chats quickly. Are you done with the part 1 of Chemical Kinetics? Like which I took 2 days back? Yes, Anish, I'm doing better, thank you. I'm doing better. So I believe everyone is done with the part 1 of Chemical Kinetics, right? Perfect. So my dear students, today it's going to be the part 2 of Chemical Kinetics, right? As I've told you in the last session, this particular chapter I'll be completing in total in 3 sessions. So first session I've already taken. Today is going to be the second session. And on Tuesday, it's going to be the third session for Chemical Kinetics, right? And at the same time, a lot of students were asking me to start the inorganic chemistry after this. Yeah. And let me tell you, from next week only, I'll be starting the inorganic chemistry. Perfect. But my dear students, those classes will happen in the special classes. Those will be the special classes on Unacademy platform, which are absolutely free of cost. I'll let you know exactly how to join those sessions, right? I'll be sharing the link with you on the Telegram group so that you remain updated about that as well. Okay? Perfect. So quickly recapping the things which we discussed in the last session, if you remember, we started with the average rate of reaction. We talked about the instantaneous rate of reaction. Then we talked about the homogeneous gaseous phase reaction carried out at constant temperature. We talked about rate of reaction on the basis of stoichiometry. Did a lot of questions based on that. And that was just the basics which is involved in the chapter Chemical Kinetics, right? Yeah. And my dear students, what all things we shall be covering today? Let me quickly give you the overview of the things. We shall be starting with the law of mass action. After completing law of mass action, we'll be going to the rate law. After rate law, we'll see the types of reactions, your elementary reactions, the complex reactions. Then we'll talk about the molecularity. We'll talk about the order. We'll exactly see how do we calculate the order of the reaction experimentally. And at the same time, we'll be covering the zero order reactions and its characteristic features as well. So this is going to be these are the topics basically which I shall be covering in the today's session. Okay? Perfect. All right, people. So without wasting a lot of your time, let's get going then. Let's get started with the today's session. So the topic which we have to cover today first, that is going to be the law of mass action. Right? Law of mass action. Let's exactly get to know what this law of mass action is all about and how do we deal with this law of mass action. My dear students, the first point about the law of mass action. What this law of mass action is all about, let me tell you, it is first of all a theoretical concept. This law of mass action, it is basically a theoretical concept. It does not have any experimental background, right? Before knowing what the law of mass action is, let me tell you this particular law of mass action concept, it is a theoretical concept. It does not have any experimental background. Point number 1. My dear students, point number 2. This law of mass action, it was basically given by two scientists. One is called as Gullberg and Laway. Gullberg and Laway. These were the two scientists who exactly gave this concept of law of mass action. Now you must be thinking what this law of mass action exactly is all about, right? What it means. Let's have a look. My dear students, as per the law of mass action is concerned, rate of the reaction is directly proportional. Rate of the reaction is directly proportional to the product of active masses, of reactants raised to the powers of their respective stoichiometric coefficients. Raised to the powers of their respective stoichiometric coefficients. Now, what it exactly means? Let's have a look what it exactly means. My dear students, try to understand one simple thing. For example, I have got a balanced chemical equation, which is like this: N1A aqueous plus N2B aqueous. Let's say it gives products. I'm assuming this as the balanced chemical equation. Let's assume that it's a balanced chemical equation, right? It's a balanced chemical equation. Now, what this law of mass action suggests? As per the law of mass action is concerned, rate of the reaction, it is directly proportional to the product of active masses of reactants. So I'll write active mass of A multiplied by active mass of B, product of active masses of reactants, raised to the powers of their respective stoichiometric coefficients. What is the stoichiometric coefficient of A? That's N1. So active mass of A raised par N1 multiplied by active mass of B raised par N2. Perfect. This is something which is your law of mass action. So basically, with the help of law of mass action, what do we get? With the help of law of mass action, we get the rate of reaction. As simple as that. And I'm sure all of you must be knowing about the fact any reactant or product which is present in aqueous form, its active mass is taken as its concentration. Any reactant or product which is present in gaseous form, its active mass can be taken either its concentration or pressure, right? And any reactant or product which will be in solid or pure liquid form, their active masses are generally taken as constant, and that constant is taken as unity to reduce the calculations. So basically any reactant or product which will be in aqueous form, its active mass is taken as its concentration. Any reactant product which will be in gaseous state, its active mass can be its concentration, or you can take its pressure as well. And any reactant product which will be in pure solid or pure liquid form, its active mass is constant, which is taken as unity, which is taken as 1 to reduce the calculations basically. Yeah? Now try to understand. My dear students, since A and B right now, they are present in their aqueous forms, right? A is present in aqueous state, B is present in aqueous state. So as per law of mass action, I can write rate of the reaction is directly proportional. I'll write active mass of A raised par N1, that is the concentration of A. Similarly, active mass of B I can write as concentration of B raised par N2. Perfect. Now, eventually you can remove the proportionality sign and you can take the constant also, right? Now, my dear students, try to understand what I'm going to say. Whenever we'll be using the law of mass action to calculate the rate of the reaction which we get with the help of law of mass action, that is something which you call as theoretical rate. Whenever you'll be given with a balanced chemical equation, and for example, you'll be using the law of mass action to calculate the rate of the reaction. Do remember, whatever rate of reaction value comes with the help of law of mass action, that rate of reaction is something which you will be calling as theoretical rate of reaction, right? That's something which you will be calling as theoretical rate of reaction. So whenever from now onwards, whenever from now onwards, for a particular reaction, you will be using the law of mass action. With the help of law of mass action, what do we get? We get the rate of reaction. And whatever rate we get with the help of law of mass action, that is something which we call as theoretical rate of the reaction. Correct? Point number 1. Point number 2. My dear students, let me tell you one more important thing. See, try to understand. Whenever I talk about the rate of reaction, rate of reaction can be measured theoretically. With the help of law of mass action. And at the same time, the rate of the same reaction, it can be measured experimentally as well. Right? It can be measured experimentally as well. Perfect. Rate of reaction, you can calculate with the help of law of mass action, or you can do certain experiments with the help of which you can calculate the rate of reaction. So basically, we have got two ways to calculate the rate of reaction. One is theoretical approach, one is experimental approach, right? My dear students, there are certain reactions in which theoretical rate and experimental rate, they come out to be equal. There are some reactions like that. But there are some reactions as well in which theoretical rate and experimental rate of reaction, they do not come equal. Right? What I'm trying to say is, we have got two ways to calculate the rate of the reaction. One is the theoretical approach with the help of law of mass action. One is the experimental approach, right? So, for example, you are given with a reaction. I'm going to calculate its rate with the help of law of mass action. So that rate is something which I call as theoretical rate. Then I'll be doing certain experiments with the help of which I'll be getting the rate of the same reaction. And that rate is something which I call as experimental rate. There are certain reactions in case of which the theoretical rate and experimental rate, they come out to be equal. But there are some reactions as well in which theoretical rate and experimental rate, they do not come out to be equal, right? Well, when you talk about the experimental rate, it is the actual rate of the reaction. Because this particular rate of reaction you have calculated with the help of experiments basically. This is the theoretical rate of reaction, right? Again, I'm telling you, there are certain reactions in which theoretical and experimental rate, they come out to be equal. But there are certain reactions in which both the two, they do not come out to be equal. What can we get from this? What are we trying to understand from this? My dear students, from this point, what I'm trying to convey that from the law of mass action, you do not always get the actual rate of the reaction. You do not always get the exact rate of reaction. You do not always get the correct rate of reaction, right? From the law of mass action, you do not always get the correct rate of reaction. So there are certain modifications which are to be done in this expression. Right? So that we can always get the correct rate of the reaction. Yes? So let me know once in the chats if it is clear. Let me know quickly in the chats if this is clear to everyone. Quickly, my dear students. So basically, again, I'm trying to tell you that there are certain reactions basically in which the theoretical rate, which is calculated with the help of law of mass action, and experimental rate, they will come out to be equal. But there are again some type of reactions in which the theoretical and experimental rate, they do not come out to be equal, right? That means from the law of mass action result, from this particular expression, you do not always get the correct value of rate of the reaction, right? So that means in order to get the correct rate of the reaction, we have to do certain changes in this expression, right? So that we always get the correct rate of reaction with the help of this particular expression, right? So that is the reason we are going to study rate law now. That is the reason we are going to understand rate law now. What is rate law exactly? Rate law, it is based on law of mass action. And as per rate law is concerned, rate of reaction is calculated Rate of the reaction is calculated by using rate law, which is an experimentally determined quantity. What it exactly means? What it exactly means? Try to understand. For example, I'm taking the reaction N1A aqueous plus N2B aqueous. Let's say it gives products. It is a balanced chemical equation, right? Now, my dear students, if you use law of mass section to calculate rate, that will give you the theoretical rate. So theoretical rate of reaction will be equal to concentration of A, it will be directly proportional to concentration of A raised power N1 multiplied by concentration of B raised power N2. Correct? But with the help of this particular result, you do not always get the correct rate of reaction. So certain modifications are to be done. And what are the modifications which we are going to do in this particular expression? In this particular expression, there are slight modifications to do, my dear students. Now, the modifications are like this. I'll be writing rate of reaction is directly proportional to concentration of A multiplied by concentration of B. Instead of N1, N2, I'll be writing X and Y. Instead of N1, N2, I'll be writing X and Y. And let me tell you, this X and Y over here, these two terms, they are measured experimentally. They are measured experimentally. Right? This is something which we call as the law of mass action. And this is something in which the powers are X and Y, which are measured experimentally. This is something which you call as a rate law, right? So what are the modifications which we exactly did? Instead of N1, we are using X. Instead of N2, we are using Y. And this X and Y, they are calculated experimentally, basically. And how they are calculated experimentally, that you'll get the idea in some time, right? So let me quickly know in the chats whether you got the difference between law of mass section and rate law, right? So from law of mass section, you get theoretical rate. From rate law, you get experimentally determined rate. Because in the rate law expression, you have got X and Y, and this X and Y, they are calculated experimentally, basically. Yeah? Perfect. People, let me know once in the chats if it is clear. Let me know once in the chats if it is super clear to everyone quickly. Quickly, my dear students. Perfect. So now, let's try to understand one thing. Let's try to understand one simple thing over here. Have a look. My dear students, for example, I'm writing a reaction. N1A aqueous plus N2B aqueous. It gives products, for example. It's a balanced chemical equation. Now, I want to write the rate law for this particular reaction. How exactly you're going to write? Rate of reaction is directly proportional to concentration of A raised per X, concentration of B raised per Y, right? Remove the proportionality sign. It's going to be a constant. Concentration of A raised per X, concentration of B raised per Y. Okay? This particular expression is something which you exactly call as, you call it as the rate law. And my dear students, this rate law always gives you the correct value of rate for a particular reaction, right? This particular rate law, it always gives you the correct value of rate of reaction. Try to understand a few more things. What this R indicates over here? R indicates the rate of reaction. What this K indicates over here? K indicates rate constant. K is something which we call as rate constant, right? Now, you must be thinking, how do we define this rate constant? Before defining the rate constant, let me tell you one more thing. Let me tell you one more important thing now to understand what exactly I'm going to say. My dear students, in order to calculate the rate of reaction, we have got two ways basically. Either I'll be using the law of mass action or I'll be using the rate law. When I use law of mass action, rate of reaction will be equal to K, concentration of A raised power N1, concentration of B raised power N2. But when I use the rate law, I'll say rate of reaction will be equal to K. It's going to be concentration of A raised power X, concentration of B raised power Y. And for example, imagine that you have got the reaction as N1A plus N2B, it gives products. This is the reaction which we have. Correct? So we have got two ways to calculate rate. Either with the help of law of mass action or with the help of rate law. With the help of law of mass action, which rate do we calculate? Theoretical rate. Which rate do we calculate here? Experimental rate. I told you in some reactions, the theoretical rate and experimental rate. Rate of reaction as per law of mass action. Rate of reaction as per rate law. In some reactions, they will come out to be equal. And those reactions in which the theoretical rate as determined by law of mass action and experimental rate as determined by rate law, those reactions in which these two terms come out to be equal. Can I say for those reactions, X will be equal to N1 and Y will be equal to N2? As simple as that, right? And for those reactions in which the theoretical rate and experimentally determined rate, if they do not come out to be equal, for those reactions, X value won't be equal to N1 and Y value won't be equal to N2. So let me know quickly in the chats if this is again clear to everyone. Quickly, my dear students. Let me know quickly if this is clear. I'll be giving you the details of it in some time, right? You'll understand it in more detailed manner in some time. Yeah? Perfect. Now, try to understand one more thing. My dear students, over here, it's time to define the rate constant first of all. How do you define the rate constant? How do we define the rate constant K for a reaction? For example, imagine that if the concentration of A is equal to the concentration of B and both are taken as 1 molar. Let's say I'm taking the concentration of A and concentration of B both as 1 molar. At that point of the time, I can say rate constant is equal to rate. Right? At that point of time, I would say rate constant is equal to the rate of reaction. So how can I define it? How can I define it? I can say rate constant is actually the rate of reaction only. It is the rate of reaction. It is the rate of reaction when the concentration of all the reactants, when the concentration of all the reactants, when the concentration of all the reactants is taken as unity, is taken as 1 molar, right? Perfect. This is how you are going to define the rate constant. So what is the rate constant basically? Rate constant is nothing. It is the rate of reaction. It is the rate of reaction when the concentration of all the reactants is taken as unity, right? So imagine, my dear students, you are taking the concentration of all the reactants 1 molar. At that point of time, you are calculating the rate of reaction. Let's imagine that you are taking the concentration of reactants and 1 molar, right? At that point of time, you are calculating the rate of reaction. So whatever rate of reaction value you will be getting, that is something which you will be calling as rate constant, right? Perfect. Is this clear to everyone quickly in the chats? Is this clear to everyone quickly in the chats, my dear students? Quickly, let me know in the chats. One more thing which I want to discuss with you. My dear students, when you write the rate law for a particular reaction, you get the powers X and Y, which are calculated experimentally. These powers have got a special name basically. These powers have got a special name. And what is the name? Let me tell you this X over here. It is called as order of the reaction with respect to. X is something which you call as order of the reaction with respect to A. Y is called as order of the reaction with respect to B. And by chance, if I add them up, X plus Y. X plus Y is something which you call as overall order of the reaction. By chance, if you add them up, this X plus Y is something which you call as overall order of the reaction, right? So what is this order exactly? Detailed explanation you'll get in some time when I'll be teaching you all this specifically, right? But right now, I would want you guys to understand few things. When you'll be given with a reaction, you'll be directly writing its rate law. In the rate law expression, you'll find certain powers which are calculated experimentally, right? When you add these powers, you'll be getting the number. When you add these powers, you'll be getting a specific number, a particular number. That number is something which you call as overall order of the reaction, right? Perfect. Right, people? And how do we get this X and Y? This X and Y, it's calculated experimentally. How it's calculated experimentally, that also will be taught in some time, right? So till now, let me know in the chats if every single thing is clear or not. Let me know quickly in the chats if every single thing is clear or not. Quickly, my dear students. Quickly, my dear students. Yeah? Perfect. Now, if you ask me about the general features, or I think we have got the slide already made here. Just a second. A slide is already made here. General features of rate constant. What are the general features of rate constant? What kind of idea the rate constant gives us? Yeah, let's get to know about that. My dear students, the first and the important point. Rate constant K. It gives us the idea about the speed of the reaction. It gives us the idea about the speed of the reaction. More the rate constant of the reaction, faster will be the reaction. More the rate constant of the reaction, faster will be the reaction. Lesser the rate constant of the reaction, slower will be the reaction. Right? More the rate constant of the reaction, faster will be the reaction. Lesser the rate constant means slower will be the reaction. Point number one. Point number two. Every single reaction has got a particular value of rate constant at a particular temperature. Every single reaction has got a unique value of rate constant at a particular temperature. So every reaction has got a particular rate constant value at a particular temperature. Yeah? Right? And at the same time, people, rate constant, it changes on changing the temperature of the reaction. When you change the temperature of the reaction, the value of rate constant changes. How it exactly changes, that is something also which we have to discuss in this chapter only, but afterwards, when I'll be teaching you Arrhenius equation, right? So right now, you just have to remember one thing. Rate constant, it is dependent on temperature. When you change the temperature of the reaction, the value of rate constant automatically changes. And you can remember one thing right now. And what is that? You can remember it like this. On increasing the temperature of the reaction, the rate constant of the reaction that increases. Why it increases? What is the logic behind that? That is something which is to be taught, right? That's something which I'll be teaching you. Yeah? Perfect? Perfect, people? So upon changing the temperature of the reaction, the value of rate constant, it automatically changes. How it changes? Why it changes? Again, that's something which is to be discussed in the Arrhenius equation, right? Perfect. And my dear students, how did we define the rate constant? What is the rate constant? It is the rate of reaction. It is the rate of reaction when the concentration of reactants is taken as 1 molar, right? So rate constant is only defined. It's only defined when the concentration of reactants is taken as 1 molar. So rate constant, it is the rate of reaction when the concentration of each reactant is 1 molar. Perfect. Now, my dear students, try to understand. The value of rate constant, should it be dependent on the concentration of reactants or not? Rate constant value, it is independent of the initial concentration of reactants. Rate constant, it is independent of the concentration of reactants, of the initial concentration of reactants, I must say, right? Because the value of rate constant, it is defined only, rate constant is defined only when the concentration of each reactant is taken as 1 molar, right? Yeah, is this point clear to you? Is this point clear to you? Is this point clear to you, people? Quickly. Is this point clear to you? Let me know once in the chats. So these are 4 important features which you need to remember about the rate constant. First of all, the value of rate constant, it gives me the idea about the speed of the reaction. More the value of rate constant, faster is the reaction. Lesser the value of rate constant, slower is the reaction. Every single reaction has got a particular value of rate constant at a particular temperature. The value of rate constant of a reaction changes on changing the temperature. And on increasing the temperature of the reaction, the value of rate constant increases, right? And since rate constant is the rate of reaction, when the concentration of reactants is taken as 1 molar, right? So my dear students, okay, let me tell you one more important thing here. Try to understand this particular point. It will automatically become clear to you. For example, you have got the reaction like this. A gives B. And over here, you have got the reaction like this. C gives D. Right? You have got the reaction like this. C gives D. Or let me write the same reaction again. A gives B. Okay? Perfect. The temperature at which the reaction is taking place is, for example, T Kelvin. Here also the temperature is T Kelvin. Right? Now, my dear students, initially, for example, you have got the concentration of A as 5 molar. This will be 0. Perfect. Let's assume initially the concentration of this reactant over here is 10 molar. This is 0. Perfect. Now, what is going to happen with time? When this reaction will start, the concentration of reactants will keep on decreasing. The concentration of reactant will keep on decreasing, right? Eventually, there will be a point when the concentration of reactant will reach 1 molar. There will be a time when the concentration of reactant will reach 1 molar. At that point of time, when the concentration of reactant will reach 1 molar, at that point of time, whatever will be the rate of reaction, that is something which you call as rate constant. That's something which you call as rate constant. Similarly, over here, the initial concentration is 10 molar. Now, with time, the concentration of reactant will keep on decreasing. There will be a time when the concentration of reactant will reach 1 molar. At that point of time, whatever will be the rate of reaction, that's something which you call as rate constant. Right? Now, you can easily imagine whether the rate constant will be same or different. No doubt, initial concentrations were different, but I have got nothing to do with the initial concentrations. Rate constant is the rate of reaction when the concentration of reactants is taken as 1 molar, right? Perfect. No doubt, whatever initial concentration of reactants you take, rate constant has got nothing to do with that. Yeah? Right, people? Right, people? Is it clear? Is it clear to everyone? Say yes or no in the chats, because this is one important point. Quickly in the chats. Quickly in the chats. Yeah? Perfect. Now, there are some types of reactions as per chemical kinetics point of view is concerned. We classify reactions into different types. Now, slowly you will see how we are going to increase the level. My dear students, we classify reactions into 2 types basically as per chemical kinetics point of view is concerned. One is called as elementary reaction. One is called as complex reaction. Right? Elementary reactions are also called as simple reactions. These are also called as simple reactions. Now, what these elementary reactions are? What exactly we have to remember about these elementary reactions? Similarly, what these complex reactions are and what do we have to remember about them? Let's get to know about that. So first of all, let's talk about the elementary reactions. Let's talk about the elementary reactions. Try to understand exactly what I'm going to say. Try to remember exactly what I'm going to say. Just give me a second. Just give me a second. Try to remember exactly what I'm going to say. First of all, those reactions which are completed in a single step. Those reactions which are completed in a single step. Those reactions are what you call as elementary reactions. Point number 1. Any reaction which is completed only in one step, you'll be calling that reaction as the elementary reaction or simple reaction. Point number 1. Point number 2 is the most important here. It is the most important here. Try to understand. Law of mass action is truly valid for elementary reactions. Law of mass action is truly valid for elementary reactions. That is, the rate expression of the reaction can be written using stoichiometric coefficients. This point is very important. Let's try to understand this. Let's try to understand this. First of all, elementary reactions are completed in a single step. Now, law of mass action is truly valid for elementary reactions. What does it mean? This is very important. Try to understand. For example, you have got the reaction like this. N1A plus N2B. It gives products. It's a balanced chemical equation. My dear students, we have got two ways to calculate the rate of the reaction. We have got two ways to calculate rate of this particular reaction. Either I'll be using law of mass action or I'll be using rate law. If I use law of mass action, I'll be getting the theoretical rate, which will come out to be rate constant, concentration of A raised per N1, concentration of B raised per N2, right? This is something which I got with the help of what? With the help of law of mass action. Now, my dear students, I can use the rate law as well. If I use rate law, I'll be getting experimental rate, which is going to be K multiplied by concentration of A raised per X, concentration of B raised per Y. This is the only difference between law of mass action and rate law. Only difference. Here the powers are stoichiometric coefficients. Here the powers are X and Y, which are calculated experimentally. Now, my dear students, in case of elementary reactions, in case of those reactions which are completed in a single step, do remember theoretical rate and experimental rate. It will be always equal. Whether you are calculating rate with the help of law of mass action, whether you are calculating rate with the help of rate law, from both the things you'll be getting the same value. What can we conclude from here? We can conclude that in case of elementary reactions, the value of X is always N1 and the value of Y is always N2. Right? That's what is written here. Law of mass action is truly valid. Law of mass action is truly valid for elementary reaction. Right? Perfect, people. Is this clear to everyone? Let me know quickly in the chats. Let me know quickly in the chats if it is super clear to everyone. Right, people? Yeah? Clear? Yes, Madhavan, we can do that. I'll tell you that in some time. Just wait for it. I hope this particular point is clear because it's important. You'll get its importance in some time. Whenever you see an elementary reaction, for elementary reactions, whether you want to calculate rate with the help of law of mass action or you want to calculate rate with the help of rate law, from both the things, you'll be getting the same result. That means X value will always come out to be N1 and Y value will always come out to be N2. Okay? I hope this particular point is clear. Now, what are complex reactions? What are complex reactions? Complex reactions are basically multi-step reactions. Those reactions which are completed in more than one step. Those reactions which are completed in more than one step. Those are what you call as complex reactions. And my dear students, the steps which are involved in the complex reaction, those are always elementary. What that means? Let me give you one example. This is one clear-cut example. This is one reaction. Okay? And my dear students, this reaction has got two steps basically. I think we have got people from Unacademy team because I texted them right now. Ajay, there is one guy who is continuously spamming the chats. His name, I'll let you know just a second. I think you already blocked him, yeah? Yeah, you have already blocked him. Is that? By the way, guys, Ajay is the one who handles the back-end team of our channel. Already done that, yeah? That's great. Thank you. Okay, listen, guys. For example, I've taken a reaction away, right? This particular reaction, it is not complete in a single step. It is complete in two steps. Try to understand. First of all, the first step is when NO reacts with Br2, it leads to the formation of NOBr2. And after that, the NOBr2, it reacts with NO, leads to the formation of NOBr. And my dear students, if you add these two steps, what do I get? If you add these two steps, NOBr2 gets cancelled out, right? NO makes it 2 times NO plus this is Br2 here. It gives what? It gives 2 times NOBr. Now tell me one thing, whether this particular reaction, whether it is completed in a single step or more than one step. Whether this particular reaction is complete in one step or more than one step. It is complete in more than one step. Any such reaction which is completed in more than one step, that's something which you call as complex reaction. That's something which you call as complex reaction. And this complex reaction, it has got how many steps? It has got 2 steps. Do remember every step involved, here is always going to be elementary. Step 1 will be elementary, step 2 will be elementary, and this net reaction is going to be complex in nature. Yeah? So do remember this particular thing as well. This was again one important point. Yeah? Well, my dear students, after discussing this, these are some basic points which we need basically afterwards. Right now, this is all basics. Something which you have to discuss actually. That's something which will be starting like in half an hour. Okay? But for that purpose, we should have the basics very strong. There is something called as molecularity. How do you define the term molecularity? My dear students, there will be a theory which we'll have to discuss in this chapter. That's collision theory basically. There is one simple statement which collision theory states. For the reaction to happen, for the reactants to form products, reacting species must collide first. Reacting species must collide first. For the reaction to occur, for the reactants to form products, as per collision theory, reacting species, they should collide first. Okay? Now, how do we define the molecularity? Molecularity, first of all, it's a complete theoretical concept. Again, it does not have any experimental background. It does not have any experimental background. It is a complete theoretical concept. Now, how it's defined? The number of reacting species, which can be your atoms, which can be ions, which can be molecules. The number of reacting species which collide simultaneously to form the product, it defines the molecularity of the reaction. For example, 2 reacting species are colliding and forming the product. We'll say molecularity of that reaction is 2. 3 reacting species are colliding simultaneously and forming the product. We'll say the molecularity of the reaction is 3, right? So the number of reacting species which collide simultaneously to form the product, that defines the molecularity of the reaction. For example, look at this particular reaction. Can I say 2 reacting species are colliding and forming the product? So I'll say molecularity of this particular reaction is 2. Simple. How many reacting species are colliding here? 2 plus 1. 3 reacting species are colliding and forming the product. Molecularity of this reaction is 3. Right? Over here, 1 molecule of this, 1 molecule of this. So 2 reacting species are colliding and forming the product. Molecularity of this reaction is 2. Right? What will be the molecularity of the first reaction? Molecularity of the first reaction will be 1. Its collision will be considered with the wall of the container. Right? Its collision will be considered with the wall of the container. Perfect. So my dear students, any reaction whose molecularity is 1, you call that particular reaction as unimolecular reaction. Any reaction whose molecularity is 2, you call it as bimolecular reaction. Right? Molecularity 3, trimolecular reaction, etc., or termolecular reaction. Okay? So, what is molecularity? Molecularity is nothing. It is a complete theoretical concept. As per collision theory is concerned, for the reaction to occur, for the reactants to form products, reacting species should collide first. The number of reacting species, which can be your atoms, which can be ions, which can be molecules, which must collide simultaneously to form the product, that defines the molecularity of the reaction. As simple as that. Now, what are the general features of molecularity? What all things we have to define for molecularity? My dear students, point number 1. Molecularity concept. The concept of molecularity. It's only defined for elementary reactions. It is not defined for the complex reactions. So, the concept of molecularity is only defined for elementary reactions. Molecularity of a complex reaction, it does not have any significance. Molecularity is the concept which is defined only for elementary reactions. Now, what are the general features of molecularity? Try to understand. Try to understand. Over here, I'm writing a statement. Molecularity of the reaction can never be zero. It can never be fractional. It can never be negative. How can you understand this? How can you understand this? For example, molecularity of the reaction is zero. What does that mean? That means zero reacting species, zero molecules are colliding. Does not have any significance. Molecularity of the reaction is negative. That means -3 molecules, -5 molecules are colliding. Is that making any significance? No. Molecularity of the reaction is 2.3, fractional. What does that mean? 2.3 molecules are colliding. Is it making any significance? Is it making any sense? No. So molecularity of the reaction, it can never be zero, it can never be fractional, it can never be negative. Okay? It can never be negative. Perfect? It can never be negative. At the same time, reactions with molecularity greater than 3, they are rarely found. Why so? Why so? Those reactions which have got molecularity greater than 3, they are rarely observed, they are rarely found. Why is that? Why is that? My dear students, what is molecularity? The number of reacting species colliding simultaneously to form the product, right? Now, for more than 3 reacting species to collide simultaneously, the probability of more than 3 reacting species to collide simultaneously is very less, right? The probability for more than 3 reacting species, for more than 3 atoms, for more than 3 molecules, for more than 3 ions to collide simultaneously is very less. That's why those reactions which have got molecularity greater than 3, they are rarely observed, right? They are not frequently observed. They are rarely observed because the probability of more than 3 molecules to collide simultaneously, it is very less basically. So those reactions which have got molecularity greater than 3, they are rarely observed, okay? At the same time, this is something which I already told you. Molecularity is defined only for elementary reactions. It is not defined for complex reactions. It's not defined for complex reactions. Okay? I hope this particular statement is absolutely clear to you. Yeah? Now we will one simple statement. One simple statement. Let's assume I've got 2 steps. These are the 2 steps which are given to me. These are, for example, 2 steps which are given to me. If I add these 2 steps, what do I get? NOBr2 gets cancelled. NO makes it 2 times NO plus Br2, it gives what? 2 times NOBr. Tell me one thing. Whether this particular reaction, whether it's completed in 1 step? No, it's completed in 2 steps. So should I be calling it elementary or complex? I should be calling it complex. Absolutely, it's a complex reaction. But few minutes back, I told you the steps which are involved to write the complex reaction, these steps are elementary. So this particular step, it is elementary. This particular step is elementary. And molecularity is defined for elementary reactions. So for step number 1, molecularity is defined. For step number 2, molecularity is defined. But for the complex reaction, molecularity is not defined. Now tell me one thing. What is the molecularity of step number 1? I would say 2 particles, 2 reacting species are colliding. Right? Similarly, molecularity of step number 2. Step number 2, molecularity is 2. What is the molecularity of the complex reaction? It is not defined at all. Yeah? Molecularity is the concept which is only defined for elementary reactions. Okay? Order of the reaction also we'll discuss in some time. Just wait for it. I'm right now defining molecularity. Is this clear to everyone, people? Quickly. Let me know quickly in the chats. Let me know quickly in the chats. Let me know quickly in the chats. Quickly. Now, I know all of you are waiting for this particular topic, that's order. So let's get to know what exactly is the order of reaction. But before going into the order of the reaction, let's quickly recap things. Molecularity, that's a theoretical concept, right? It's only defined for elementary reactions. Number two, for the reaction to happen, the reacting species should collide first. The number of reacting species which collide simultaneously to form the products, that defines the molecularity, right? Those reactions with molecularity 1, unimolecular, molecularity 2, bimolecular, etc. Right? Molecularity of the reaction can never be 0. It can never be negative. It can never be fractional. Those reactions which have got molecularity greater than 3, they are rarely observed. Why is that? Because the probability of more than 3 reacting species to collide simultaneously, that's very less. That's the reason why those reactions whose molecularity is greater than 3, why those reactions are rarely found. Right? One more thing where you can mess up. For example, you have got a reaction like this. Half of H2 plus half of I2. It gives HI. If I ask you what is the molecularity of this reaction, I'm sure you'll make a mistake here. What is the molecularity of this reaction? Quickly in the chat. Quickly in the chats. Quickly in the chats. Do you think its molecularity is 1? Because half is equal to 1? You're not going to do that. My dear students, if by chance you get this sort of a reaction, so your first point should be, your first focus should be to convert this fraction into a natural number. What I'll be doing, I'll be multiplying this reaction throughout by 2. If I multiply this reaction throughout by 2, it becomes H2 plus I2 gives 2 times HI. Now tell me the molecularity of this particular reaction. I would say molecularity of this particular reaction is 2, right? So you can directly say molecularity of this reaction also has 2. Perfect. Don't say the molecularity of this reaction is 1. It's 2. Okay. So your first point should be, your first focus should be to convert the fraction into natural number. And you will be getting a new reaction here. Whatever is going to be the molecularity of this new reaction, same is going to be the molecularity of this particular reaction, which you were supposed to calculate. So don't make a mistake here also. All right, let's talk about something which is very important. That's order. How do you define the order? What is order basically? My dear students, order is basically defined as the sum of powers. Order is basically defined as the sum of powers. Sum of powers of the concentration terms. Involved in the rate law. What does that mean? Let's have a look. For example, you have got the reaction like this. N1A plus N2B, it gives products. It is a balanced chemical equation, I believe. It's a balanced chemical equation. Let's assume rate constant of this particular reaction is K. Now, my dear students, I am going to write the rate law for this reaction. Rate law for the reaction, R is equal to K, concentration of A raised per X, concentration of B raised per Y. Should I be calling this as a rate law? Absolutely, it's a rate law, right? In the rate law, you are seeing there are 2 concentration terms here, and their powers are X and Y. This X is something which I call as order of the reaction with respect to A, and Y is something which I call as order of the reaction with respect to B. And if I add them up, this X plus Y is something which you call as overall order of the reaction. Right? So what is order? Order is basically a number. Right? Order is defined as the sum of powers of all the concentration terms involved in the rate law. That defines the order of the reaction. Now you must be thinking, what kind of idea this order gives us? That also will be discussed. What kind of idea this order will give us? What kind of idea this order can give us? Before talking about that, let me tell you, in order to calculate the overall order of the reaction, are we supposed to write the rate law? Absolutely, we are supposed to write the rate law. Is the rate law theoretical or experimental? Rate law is experimental. Therefore, order. Is it theoretically determined or experimentally determined? Order is an experimentally determined quantity. It's an experimentally determined quantity. It's an experimentally determined quantity. Okay. Now, people, at the same time, when I talk about order, it can be 0. Order of the reaction can be 0. And any such reaction whose order is 0. Whose order is 0. What does that mean? Any reaction whose order is 0. What does that mean? Order is 0. That means x plus y is 0. That means x plus y is 0. For example, one of the cases, x value is 0, y value is 0. If x is 0, y is 0. That means R will be equal to K. That means for those reactions, rate of reaction will be independent of the concentration of reactants. Right? Order can be 0 also. And for those reactions, rate of reaction will be independent of the concentration of reactants. Okay? So order, it can be 0. Order can be positive as well. Order can be fractional as well. Order can be fractional as well. For example, any reaction whose order is 0, you call that as 0 order reaction. Any reaction whose order is 1, you call that a first order reaction. Any reaction whose order is fractional, you call that as a fractional order reaction. You call that as fractional order reaction. So unlike molecularity, order can be 0, it can be positive, it can be fractional as well. Now people, one more important thing. Let me tell you order with respect to any reactant. Order with respect to any reactant. It can be negative. It can be negative. Order with respect to any reactant, it can be negative. But overall order of the reaction can never be negative. Can never be negative. What does that mean? That means x can be negative, y can be negative, but x plus y, its value will never come out to be negative. Right? Order with respect to any reactant can be negative. X can be negative, y can be negative, but do remember x plus y value, it is never going to be negative. X plus y value, it's never going to be negative, right? It's never going to be negative. Now, there is one very, very, very important thing. There is one very, very, very important thing. First of all, have a look on this particular slide. This is order definition. In order to calculate order, what do we need to write? We need to write rate law. Rate law is experimentally determined. That means order, it is also experimentally determined. Order can be 0, it can be positive, it can be fractional. Order can be negative with respect to any of the reactant, but overall order of the reaction can never be negative. This is the important point, guys. For an elementary reaction, order is equal to molecularity. Now, how can you justify it? How can you justify it? How can you justify this particular statement? For the elementary reaction, order is equal to molecularity. What does it mean? Try to understand. For example, you have got the reaction like this. 2 times A plus B, it gives C. It's a balanced chemical equation, for example. And I'm assuming that the reaction is elementary in nature. The reaction is elementary in nature. We know molecularity is defined for elementary reactions. So what will be the molecularity of this reaction? 2 plus 1, 3. Molecularity of this reaction is 3. Okay? Molecularity of this reaction is 3. Do you remember? Law of mass action is truly valid for elementary reactions. So my dear students, if you want to calculate the rate of this particular reaction, I would say the theoretical rate and experimental rate will be the same. The theoretical rate and experimental rate will be the same. Why? Because it's an elementary reaction. I have mentioned already, in case of elementary reactions, x value is equal to n1 and y value is equal to n2. Perfect. What is n1 value? n1 value is 2. What is n2 value? n2 value is 1. Perfect. So x value is equal to 2. Y value is equal to 1. So what is the overall order of the reaction? I would say overall order of the reaction will be x plus y. So 2 plus 1, 3. Now people, what was the molecularity of the reaction? 3. What is the overall order of the reaction? 3. So do remember, whenever you see an elementary reaction, in case of elementary reactions, order has to be equal to its molecularity. Order will be equal to its molecularity, right? You can understand it like this also. In order to calculate order of this reaction, what do I need to write? I need to write the rate law. Rate law is equal to R is equal to K, concentration of A multiplied by concentration of B, raised for X and Y. But in case of elementary reactions, instead of X and Y, you use the powers. So this is 2, this is 1. So overall order of the reaction will come out to be 2 plus 1, which is 3. Perfect. So this is one very important statement, right? For the elementary reactions, order is equal to molecularity. Okay. Now, tell me one thing. Is this particular statement correct or not? What do you think? Is this particular statement correct or not? A zero order reaction must be complex. Can't a zero order reaction be elementary? What do you think? I'm asking you. I'm asking you. Can't a zero order reaction be elementary? Say yes or no, whether this particular statement is right or wrong. I'm waiting for your answers in the chats. What do you think? It's absolutely correct statement, guys. A zero order reaction must be complex. It is absolutely correct. Why? I'm telling you, a zero order reaction can never be elementary. I'm telling you, a zero order reaction can never be elementary. It's always going to be complex. Because if the zero order reaction was elementary, at that point of time, its order and molecularity should have been same. If the zero order reaction was elementary, then its order and molecularity should have been same. Since I'm talking about zero order reaction, that means those reactions whose order is zero. Order no doubt is zero, but can molecularity be zero? Molecularity cannot be zero. Molecularity cannot be zero. Molecularity cannot be zero. Gentle shots, just wait for all these things. I did not discuss everything in detail yet. This is just the basics. Whatever you're asking for zero order reactions, rate does not depend on the concentration. For the first order, they depend. Second order, they depend, right? So just wait for it. Let me complete the basics, then we'll move on. We'll summarize all the things together. Okay, tell me one thing, guys. So is this particular statement absolutely correct? A zero order reaction, it can never be elementary. Because if the zero order reaction is elementary, then its molecularity has to be zero. Molecularity is equal to zero, does not have any significance. Right? All right. Among these two statements, tell me which statement is perfectly correct. Among these two statements, which statement is correct? Among these two statements, which statement is correct? First statement is a unimolecular reaction must be first order. A unimolecular reaction. That means that reaction whose molecularity is 1. A unimolecular reaction must be first order. Is it necessary that any reaction whose molecularity is 1, its order will be also 1? It is a must condition only when the reaction will be elementary in nature. It is the must condition only when the reaction will be elementary in nature, right? So first statement, it's not correct, but second is correct. A unimolecular elementary reaction, its order will be always 1, right? Its order will be always 1. Okay? I hope you got this particular point as well, right? So this was just the idea of order. Now, before solving the questions based on order, before letting you know the significance of the order, let me tell you one more simple thing. A relation between different rate constant. Relation between different rate constant. Try to understand. My dear students, for a particular reaction, we always have got a rate constant. For a particular reaction carried out at particular temperature, every reaction has got a particular value of rate constant. So K reaction represents a rate constant of the reaction. Now I'm defining few more things. I'm defining Ka. Ka is something which you call as rate constant for disappearance of A. Ka is something which you call as a rate constant for disappearance of A. For example, I'm writing Kb. Kb is something which you call as a rate constant for disappearance of B. For example, Kc. Kc is called as a rate constant for appearance of C. And similarly, Kd is called as a rate constant for appearance of D. Now, my dear students, there is a particular result which relates rate constant of reaction and all these individual rate constants. There's a particular result. I'm not going to derive that. I'll be giving you that result directly. Do remember rate constant of the reaction. Sorry. Rate constant of disappearance or appearance. of reactant product is always equal to rate constant of reaction multiplied by stoichiometric coefficient of reactant product. This is the particular result which you are going to remember. It has got derivation as well. No need to go into the derivation. Just remember the result, utilize the result. For example, if I write Ka is something which I call as rate constant of disappearance of A. It will be equal to rate constant of reaction multiplied by stoichiometric coefficient of A, that's N1. Similarly, Kb, rate constant of disappearance of B, is equal to rate constant of reaction multiplied by N2. Similarly, Kc, it will be equal to rate constant of reaction multiplied by N3. Similarly, Kd will be equal to rate constant of reaction multiplied by N4, right? So do remember how to write the relation between rate constant of the overall reaction and rate constant of individual rate constant. Yeah? Okay. Now, if you got it, what should be the answer of this particular question as per you? What do you think? What do you think should be the answer of this question? Find the relation between K1, K2 and K3. K1 is the rate constant of disappearance of A. K2 is the rate constant of disappearance of B. K3 is the rate constant of appearance of C. Okay. Now, if I ask you, what is K1? K1 will be rate constant of reaction multiplied by stoichiometric coefficient of A. That's 2. K2 will be equal to rate constant of reaction multiplied by stoichiometric coefficient of B. K3 will be equal to rate constant of reaction multiplied by stoichiometric coefficient of C. Right? Perfect. You got 3 equations. Now, from this particular equation, what is K reaction? Rate constant of reaction. That will be K1 by 2. From the second result, rate constant of reaction will be equal to K2 divided by 3. From this particular expression, rate constant of the reaction is equal to K3. Now, a reaction always has got a particular value of rate constant. Rate constant of reaction, reaction. So from first, second and third, you can say K1 divided by 2 has to be equal to K2 divided by 3, which has to be equal to K3. Okay. Now take the LCM of denominators. LCM of denominators will come out to be 6. So multiply with 6, multiply with 6, multiply with 6. So this is 3 times K1 is equal to 2 times K2, which is equal to 6 times K3. So this is the relation between K1, K2 and K3 which you were supposed to calculate. Is this clear? Is this clear, people? Is this clear? Let me know once in the chats quickly. Everyone. Yeah? Okay. I hope this is clear to everyone. Now guys, one more simple thing. Right now I'm teaching you small things. So that once you get to know these small things, there will be no issue in understanding the actual stuff. Right? Which you might find a bit complicated. Okay, units of rate constant. What are the units of rate constant? For example, you have got the reaction A gives B. This is the reaction, for example. Let's assume that order of the reaction is equal to N. Okay, let's assume that order of the reaction is equal to N. First of all, see, you have got only one reactant here. Can I say, in this particular reaction, whatever is the order with respect to A, whatever will be the order with respect to A, same is going to be the overall order of the reaction. So order with respect to A and overall order of the reaction, both are going to be same because there is only one reactant, right? Let's assume the order of reaction is N. Let's say the rate constant is K. Can you write the rate law? Rate law will be equal to. It is going to be K. The actual rate law is active mass of A raised per what? Active mass of A raised per N. This is the actual rate law, right? This is the actual rate law. Now, for example, this A was in aqueous state. If A is in aqueous state, you can say R is equal to K, concentration of A raised per N. For example, this A was in gaseous state. You can say R is equal to K. Instead of active mass of A, you can write pressure of A raised per N. Right? You can use both the things. Even for example, if it is a gas, if A is the gas, for example, for gases, you can write rate law like this or like this. Because for gases, active mass is concentration as well as pressure. For gases, we define pressure as well as concentration. Okay. Now tell me one thing. So what will be K over here? K will be equal to R divided by concentration of A raised per N. What will be K over here? It's going to be R divided by pressure of A raised per N. Right? So units of K. Units of rate here are going to be moles, liter inverse, moles, liter inverse. For example, time is in seconds, so second inverse. Units of rate, moles, liter inverse, second inverse. In the denominator, we have got concentration. Concentration is moles per unit volume. So it's going to be moles, liter inverse, raised per n, right? So I would say the overall unit of K will be equal to moles, liter inverse, raised per 1 minus n. And if time is in seconds, then second inverse. What is n? N defines the order of the reaction. Or if you want to use this particular expression, rate, its units can be atm second inverse. For example, if pressure is in atm, time is in seconds, divided by pressure is in atm, so atm raised per n, right? So it has to be atm raised to the power 1 minus n and second inverse. So these are the general units of rate constant which I would want you guys to remember. General units of rate constant which I want you guys to remember. Yeah? Right, people? Okay. Now try to understand one thing. Let's assume you have got a zero order reaction. For a zero order reaction, n is equal to 0. If n is equal to 0, what will be the units of rate constant? It's going to be moles, liter inverse, second inverse. Or if you want to use this result, if n is equal to 0, it's going to be atm second inverse, for example. Yeah? My dear students, if you have the first order reaction, if n is equal to 1, first order reaction, what are going to be the units of rate constant? If n is equal to 1, 1 minus 1 is 0, anything raised for 0 is 1. It is directly going to be second inverse. Or the time inverse. It can be second inverse, minute inverse, hour inverse, right? If you want to use this particular expression, again it's going to be second inverse only, or minute inverse, or hour inverse, whatever, right? So indirectly, time inverse. Okay? If you have the second order reaction, n is equal to 2, put the value of n as 2, So rate constant units will be moles, liter inverse, raised par. 1 minus 2 is minus 1. It is minus 1. And second inverse. Or here you can write atm raised par minus 1. With it, you can write second inverse. So based on the order of reaction, you have to write the units of rate constant. Okay? Do remember this particular scenario as well. Perfect? Perfect, guys? Now, if you ask me, what kind of idea this order gives us? What kind of idea order of the reaction gives us? My dear students, order of the reaction is going to let you know. Order of the reaction is going to let you know how many times the rate of reaction will change. How many times rate of reaction will increase or decrease upon changing the concentration of reactants. How exactly? For example, I'm assuming that it is a zero order reaction. I'm assuming that order of this reaction is 0. For example, you have got one more reaction, C gives D. I'm assuming that order of this particular reaction is 1. Perfect. Can you write rate law for this? Absolutely. R is equal to K, concentration of A raised power 0. Write rate law for this. R is equal to K, concentration of C raised power 1. Right? Anything raised power 0 is 1. So R is coming out to be K. Okay, R is coming out to be K for the first reaction. And R is equal to coming out to be Kc raised power 1. Okay. Now tell me one thing. If you double the concentration of A, what will happen to rate of reaction? Rate of reaction is independent of concentration of A. If you double the concentration of A, nothing will happen to the rate of reaction. But here, if you double the concentration of C, the rate will double. Okay? Here nothing happened. But here something is happening. So, what was the difference? Order of the first reaction was 0. Order of the second reaction was 1. And here you are observing that upon doubling the concentration of reactant, nothing is happening to the order. Sorry, nothing is happening to the rate. But upon doubling the concentration of C for this reaction, upon doubling the concentration of this reactant, rate of reaction is doubling. Okay? For example, you have got a reaction. E gives F. Let's assume order of this particular reaction is 2. Can you write rate law? R is equal to K, concentration of E raised power 2. Correct? Now, if you double the concentration of reactant, 2 2s are becomes 4. Rate becomes 4 times. For this particular reaction, upon doubling the concentration of reactant, rate becomes 4 times. So order, what kind of idea it's giving you? It's simply giving you the idea how many times the rate of reaction changes upon changing the concentration of reactant. You getting it? Are you getting this? Is it clear? So order is letting me know simply like how many times the rate of reaction changes upon changing the concentrations. Our next session is on Tuesday. Perfect. Manikanda, you can just drag the video a little back. It will be a replay for you. Okay. There is no need to repeat. It's a live session. All right. Let's solve some basic questions based on order. Basic questions, I'm telling you. Look at this particular question. As far as this question is concerned, for a chemical reaction A gives B, it is found that the rate doubles when the concentration of A is increased 4 times. Find the order of the reaction. How do you solve these sort of basic questions? My dear students, you are given with the reaction A gives B. You are given with the reaction A gives B, whose rate constant is K. Let's assume that since there is only one reactant here, so order with respect to A has to be the overall order of the reaction. Let's assume that the overall order of the reaction is equal to N. Let's assume that the overall order of the reaction is equal to N. If you got to know the overall order of the reaction is equal to N, can you write the rate law for the reaction? Rate law for the reaction, R is equal to K, concentration of A raised to the power 2. This is rate law. Correct? Let me call this as equation number 1. Let me call this as equation number 1. Now, as per the question, it is found that the rate doubles. It is found that the rate doubles. Initially, the rate was R. Now, it is becoming 2 times R. It is becoming 2 times R. When is it becoming 2 times R? When is it becoming 2 times R? When the concentration of A is becoming 4 times. Earlier, the concentration was A. Now, it is becoming 4 times A. Let me call this equation number 2. Why am I writing 2 here? It's N, right? Because order of the reaction is N, right? Perfect. So, how many equations I made? I made 2 equations. Yeah. Now, my dear students, it's time to solve these equations. Divide equation 2 by equation 1. When you divide equation 2 by equation 1, R gets cancelled. So, on left side, you have got 2. K gets cancelled. A power n cancelled. On right side, you have got 4 raised power n. What should be the power of n? What should be the value of n such that LHS RHS becomes equal? What should be the value of n such that LHS RHS will be equal? So n value has to be 1 by 2 such that 4 raised power 1 by 2 will come out to be 2. So n value is equal to 1 by 2. And what was this n exactly? N was the overall order of the reaction. Yeah? N was the overall order of the reaction. Okay? That's something which you were supposed to calculate. Is it clear? So you should be able to solve these sort of questions as well. Let me solve one more. Look at this question. Look at the question carefully. Try to solve this. The rate of the reaction becomes half when the volume of the vessel is doubled. Find the order of the reaction. So you are doubling the volume of vessel. We have to see what will happen to the rate of the reaction. Sorry, we have to see what is the order of the reaction. The reaction is given to me. The reaction is given to me. My dear students, this particular reaction, which is given to me, let's assume that its order is equal to N. If its order is equal to N, can't you write its rate law? Its rate law has to be R is equal to K. Concentration of A raised power N. Concentration of A raised power N. This is the rate law, correct? Now, my dear students, what is concentration basically? Concentration is moles per unit volume, right? So I can write the same equation as R is equal to K. Instead of concentration of A, I can write moles of A divided by total volume of the system in liters raised power N. Let me call this as equation number 1. Now, as per the equation, the rate of the reaction becomes half. Initially, the rate was R. Now, it is R by 2. The rate of the reaction becomes half. When the volume of the vessel is doubled. Initially, the volume of the vessel was V. Now, it's 2 times V. Now, it's 2 times V. Let me call this equation number 2. Now, divide the 2 equations. You're done, right? Divide the 2 equations. For example, dividing 1 by 2. Dividing 1 by 2. So, R divided by R by 2. R by 2, R gets cancelled. On left side, you get 2, right? What is something which you'll be getting on the right side? This and this gets cancelled. NA divided by V raised power N, NA divided by V raised power N gets cancelled. So here what do we get? Here what do we get? We get 2 raised per n here, right? We get 2 raised per n here. Perfect. That's the only thing which is left. Now compare these two. So n value has to be equal to what? N value has to be equal to 1. So what was n? N was the overall order of the reaction, right? I hope this particular equation is also clear to you. Right, people? I hope this particular question is clear. These are 2 more questions. Look at these questions. We are given with some random rate law, something like this. A reaction is given. Calculate the order of reaction. If the concentration of Br2 is very high, if the concentration of Br2 is very less. My dear students, just remember one thing. For example, if these conditions were not specified, imagine if these conditions were not specified, then your answer will be directly, order cannot be predicted. It's a complicated rate law, something, I don't know what's mentioned here. If the conditions are not mentioned in this type of the rate law, this is the rate law which is given, then directly what you will be doing? Can you all see me? Am I audible, visible to you? Yeah? Just say once in the chats. Can you all see me? Am I audible, visible? Quickly, everyone. Everyone in the chats once quickly. Okay. See now. What I'm trying to say, if the conditions are not specified, then your answer will be directly, the order cannot be calculated. But right now the conditions are mentioned, so order can be calculated. The first question. The first question is, calculate the order of the reaction if concentration of Br2 is very high. So we are assuming that the concentration of Br2 is very high. Okay. What is the rate law that's given to us? R is equal to K1 multiplied by concentration of H2 multiplied by concentration of Br2 raised power 1 by 2 whole divided by its concentration of Br2 plus K2 multiplied by concentration of HBr. This is the rate law is given. Now the first condition suggests that the concentration of Br2 is very high. My dear students, if the concentration of Br2 is kept very high, so in the denominator, can't you neglect this term? This particular term can be neglected because the concentration of Br2 is very high. And if the concentration of Br2 is very high, that means in place of concentration of Br2 plus K2 multiplied by concentration of HBr, you can only write concentration of Br2. Correct? Now write the rate law again. Rate law will be equal to R is equal to K1 concentration of H2 multiplied by concentration of Br2 raised power 1 by 2. And in the denominator, we'll be only having Br2 raised power 1, which can be mentioned as K1 as such, concentration of H2 as such, Br2 raised power 1 by 2, and Br2 raised power 1, which has to be equal to Br2 raised power minus 1 by 2. Right? Powers are, bases are same, powers are subtracted in case of division. Okay. Now, my dear students, look at this particular rate law. Look at these concentration terms. Look at their powers. So I'll say order with respect to H2 is 1, order with respect to Br2 is minus 1 by 2. So I would say the overall order of the reaction will be equal to X plus Y. X plus Y. The value overall will come out to be 1 by 2. So 1 by 2 is the order of the reaction whose rate law was given to me and whose concentration of Br2 was kept very high. Okay. The second part I'm sure you can do easily. If the concentration of Br2 is kept very less, and if the concentration of Br2 is kept less, that means instead of Br2 plus K2 HBr, you'll be only writing K2 HBr. Right? So let me show you that part as well. Because you might get confused. To solve the second part. Try to understand the second part, guys. In the second part, he is saying that if the concentration of Br2 is very less, if the concentration of Br2 is very less, for example, if it is very less, that means in place of Br2 plus K2HBr, what you'll be writing? You'll be writing K2HBr only because Br2 is very less. Okay. Now, write the rate law again. So, rate law is equal to R is equal to K1, concentration of H2 raised power 1, concentration of Br2 raised power 1 by 2. And in the denominator, in place of this whole term, you'll be only writing K2 multiplied by concentration of HBr. Clear? So, R is equal to, this is constant, this is constant. Division of two constants will make it a new constant, K dash for example. And this is H2 raised power 1, Br2 raised power 1 by 2. And this will be HBr raised power minus 1. I took HBr in the numerator, right? So, this is my perfect correct rate law now. So, I'll say order with respect to H2 is 1, order with respect to Br2 is 1 by 2, order with respect to HBr is minus 1. So, what about the overall order of the reaction? Overall order of the reaction now will be equal to 1 plus 1 by 2 plus minus 1. The overall order of the reaction again will be 1 by 2 only. Okay? So, you should be able to solve these sort of questions also. Sometimes they'll be giving you the complicated rate law form. If the conditions are not mentioned, then write the order cannot be calculated. Right? If the conditions are specified like this, then you can calculate the order. Is this clear? Say yes or no in the chats quickly. Say yes or no in the chats quickly, my dear students, if this is clear. Yeah? Perfect. Now, let's get to know how order is calculated experimentally. How do we get the value of X and Y experimentally? There is a trick also, but there is a general procedure as well. So first, I'll go ahead with the general procedure. Then I'll let you know the trick also with the help of which you can calculate the order easily. Okay? My dear students, look at this particular question. In this particular question, we are given with a reaction. This is the reaction that's given to us. And there are 3 experiments which have been carried out in the lab for this particular reaction. When the concentration of NO is kept this much, when the concentration of H2 is kept this much, at that point of time, rate of reaction was this much. Similarly, the experiment was repeated. Concentration of NO was kept this much, H2 concentration, this rate of reaction was coming out to be this much, right? Similarly, the third experiment. So 3 experiments have been carried out. 3 experiments have been carried out. In the first experiment, this is the rate. Second, this is the rate. Third, this is the rate. We have to check what is the order of the reaction. How do you calculate the order here? Understand. First thing, in order to calculate the order, what do we need to write always? We need to write the rate law. So write the rate law for the given reaction. R is equal to K, concentration of NO raised by X, concentration of H2 raised by Y. This is your rate law first of all. Yeah. Now in this rate law, select the data which is given in the first experiment. In this rate law, fit the data which is given in the first experiment. As per the first experiment, what about the rate? The rate is 3 into 10 raised by how much? 3 into 10 raised by minus 5 moles per liter per second is equal to K. What is the concentration of NO kept in the first experiment? That is 5 into 10 raised by minus 3 raised by X. Concentration of H2, that is 2.5 into 10 raised by minus 3 raised by Y. So this is I call as equation number 1. Equation number 1. Now similarly, you can make the second equation. Fit the second experiment data in this particular equation. R value will be equal to 9 multiplied by 10 raised by minus 5 is equal to K. Concentration of NO. NO concentration is 15 multiplied by 10 raised by minus 3 raised by X. Concentration of H2 in the second experiment, that's 2.5 into 10 raised by minus 3 raised by Y. You call this as experiment number 2. Equation number 2. What about equation number 3? That will be equal to equation number 3. 36 multiplied by 10 raised by minus 5 is equal to K. It's going to be 15 multiplied by 10 raised by minus 3 raised by X. And it's going to be 10 multiplied by 10 raised by minus 3 raised by Y. Calling this as the third equation. So how many equations I got? I got third equations, right? My dear students, we have to solve these 3 equations and get the value of X and Y. You can easily do that. Let's try to see what to do. For example, if I'm dividing 2 and 1, I'm dividing 2 and 1. Equation 2 divided by equation 1. What do I get? 10 power minus 5, 10 power minus 5. Cancel. 9 by 3 is 3. On LHS, you have got 3. Now, this whole term is cancelled. 10 raised power minus 3, 10 raised power minus 3 cancelled. 15 divided by 5 is 3. So it's going to be 3 raised power x. Now tell me, from this particular equation, can't I say x value has to be 1? X value has to be 1, then only LHS, RHS will be equal. So I got the value of x. I got the value of x. Now it is time to get the value of y. It's time to get the value of y. So what exactly I'll be doing? I will be doing one thing. Third equation divided by second equation. 3 divided by 2. So this term cancel. 36 divided by 9. That comes out to be 4 is equal. This term cancel. K cancel. 10 raised power minus 3, 10 raised power minus 3 cancel. 10 divided by 2.5 is 4. So it's 4 raised power y. So 4 is equal to 4 raised power y. So what has to be the value of y? Such that LHS RHS is equal. So y value has to be 1. Right? So x value you got, y value you got. So what should be the overall order of the reaction as per you? It has to be x plus y, 1 plus 1. That comes out to be 2. So overall order of the reaction is equal to 2. Yeah? Perfect. Is that clear, people? Is it clear? Quickly. Quickly, guys, quickly. Perfect. Okay, try to understand one more simpler way of solving the same question. Try to understand one more simpler way of solving the same question. Since you got to the actual procedure, right? If you try to solve the same question without using pen and paper, what do you need to do? See, rate law already you know. R is equal to K, concentration of NO raised power X and concentration of H2 raised power Y. This is the rate law which you already know. Now, my dear students, look at the experiments. If you see, in the first and second experiment, concentration of H2 is kept same. In the first and second experiment, concentration of H2 is kept same, right? Okay. So, what you need to do, imagine as if in this expression there is no H2. Imagine as if there is no H2 in the expression. Now, when you are moving from first to second, what is happening to the concentration of NO? I'll say concentration of NO is increasing 3 times. From first to second, concentration of NO is increasing 3 times. At the same time, look at the rate value. Rate is also increasing 3 times. Yeah? Right? Right, people? So, when you look at first and the second experiment, the concentration of H2 is kept same. So, imagine as if H2 is not here. Now, NO concentration is being increased 3 times and rate of reaction is also increased 3 times. So imagine H2 is not here. You're increasing the concentration. You're increasing the concentration of NO 3 times. Leave this part aside. You're increasing it 3 times. And eventually, rate is also coming out to be 3 times. Rate is also increasing 3 times. When is it possible? It is possible only when the value of x is 1. Because 3 raised power 1 is 3. If the value of x was 2, then 3 square has to be 9. If the value of x was 2, then on making this 3 times, rate has to be 9 times. But it's observed that on increasing NO concentration 3 times, the rate is becoming 3 times. The rate is increasing 3 times, right? So directly the value of x is 1. Perfect. Now similarly, look at experiment number 2 and experiment number 3. NO concentration is kept same. So imagine NO is not here. Imagine NO is not here. Now, when you move from here to here, the concentration of H2 is increased 4 times. Look at the rate. The rate is also increased 4 times. The concentration of H2 is increased 4 times. And the rate is also increased 4 times, which is possible only when the value of y is 1, right? Because if the value of y was 2, then 4 square should have been 16. Then rate should have been increased 16 times, but that's not the case here, right? Perfect. Is that clear? Is it clear, people? Quickly in the chats. Is it clear, guys? Say yes or no in the chats. You got to know how to solve the equation like this. We have got a lot of spammers today. Let them come, let them come. Go ahead, bro. Go ahead. Quickly, people in the chats, is it clear? Perfect. Let's try to solve one more question like this. Let's try to solve one more question like this. Look at this particular question. General procedure, I hope you already know. Yeah. General procedure, I hope you guys know. Let's solve the question. Right? Let's solve the question with the help of direct result. I mean, the direct shortcut which I told you. First of all, the reaction is given to us. Rate law will be equal to R is equal to K. Concentration of NO raised per X, concentration of Cl2 raised per Y. Correct? Now look at the first and second experiment. NO is kept same. Concentration is kept same. This is increased 3 times. Rate is increased 3 times as well. So on making the concentration 3 times, on increasing the concentration 3 times, the rate is also increasing 3 times, which is only possible if the value of X is 1. So you got the value of X. You got the value of X, that's 1. Now get the value of Y. Get the value of Y, guys. Get the value of Y. Now, first of all, look at the 3 experiments again. Now try to see experiment number 1 and 3. Cl2 concentration is kept same. The concentration of NO is made 3 times here. NO concentration is increased 3 times. And rate is becoming 9 times. Concentration of NO is increased 3 times. Concentration of NO, just a second, guys. Sorry. Wait. Cl2, this is NO. X is not 1. I think Y is 1. Right? The concentration of Cl2. Okay, we were increasing the concentration of Cl2. So it's Y value that's 1. It was Y value that was 1. Now look at the second case. NO concentration is increased 3 times, rate is becoming 9 times. NO concentration is increasing 3 times, right? And rate is becoming 9 times, which is only possible when the value of X is 2. Because 3 ka square then only will come out to be 9, right? So X is 2, Y is 1. So overall order of the reaction is 3. That's all. Well, you can use the same procedure, the basic procedure as well. Yeah? Right? Is it clear? Perfect, people. Is it clear? Say yes or no quickly in the chats. Perfect. So I hope from now onwards, easily, you can solve the questions based on experimental determination of rate. Okay? Now, second order reaction and pseudo first order, they are different. They are not same. I think we'll take a break for like 15 minutes. Then after 15 minutes, we'll get back. Okay? So the time right now is 7:41. So session will resume at session resumes at 8:05 p.m. I want everyone to be back because now we are going to start the actual scenario. Till now, whatever I was teaching you, that was complete basics. Now it's going to be the real stuff which I'll be teaching you, right? In which students get a lot of problems. And this is something which I'll be dealing in detail, right? So zero order reactions, integrated equation, and the characteristic features and the types of problems. So be back at 8:05 sharp, guys. Till then, you have some tea. That's what I'm also going to have. See you in a while. Take care. So guys, can you see me again? Am I audible, visible to everyone? Yes. Are you all back? Perfect, guys. Perfect. So let's start then. Right? Let's start with zero order reactions. Just give me a second. All right. So I'm marking the heading over here as zero order reactions. Zero order reactions. This is one important topic, right? So my dear students, how do we first of all define the zero order reaction? Let me mark its definition first. Then I'll make you understand what these zero order reactions exactly are all about. Yeah? Talking about its definition. The reactions in which rate of reaction is independent of the concentration of the reactant. What it means, you'll get the idea in some time. Have a look, people. For example, imagine that you are given with a reaction that is A gives B. Imagine it is one balanced chemical equation. A gives B. I'm assuming that the rate constant of this reaction, for example, is K. And at the same time, I'm assuming that the order of the reaction is 0. Order of the reaction is 0, right? So first of all, before talking about the actual stuff here, let me make you clear with few new terminologies. First, I'm starting at time t is equal to 0. At time t is equal to 0, the reaction has not started yet. There is no product formation yet. Let's assume that initially at time t is equal to 0, the concentration of reactant, for example, that is A0. So what will be the concentration of product? Concentration of product at time t is equal to 0 will be absolutely 0, right? Now, my dear students, when the reaction will start, what will happen to the concentration of reactant? Concentration of reactant will keep on decreasing and concentration of product will keep on increasing. Let's assume at time t, the concentration of reactant left, that is AT, and the concentration of product formed, that is BT. So first of all, be careful with all these terminologies. What A0 is, what AT is. So let me write it over here. What is A0? A0 is basically the concentration of reactant at T is equal to 0. What is AT? AT is basically the concentration of reactant left at time t. The concentration of reactant left at time t, right? So initially the concentration of reactant is A0. At time t, the concentration of reactant left is AT. Now, for example, I want you guys to write the rate law for this particular reaction. Can you write the rate law? You should be able to write. Rate of the reaction as per rate law is equal to rate constant multiplied by concentration of reactant raised power 0, because the order of the reaction is 0. See, anything raised power 0 is 1. So what does that mean? Is the rate dependent on the concentration of reactant? No. Rate is independent of the concentration of reactant. If you increase or decrease the concentration of reactant, nothing will happen to the rate. Any such reaction in which the rate will be independent of the concentration of reactant, you call that particular reaction as the zero order reaction. Okay, point number one. Point number two. My dear students, is there any other way to calculate the rate of reaction? Absolutely, you can use the differential form as well. I'll say rate of the reaction is equal to, with respect to A is the reactant. So start with minus sign. 1 by stoichiometric coefficient. Stoichiometric coefficient is 1. Change in the concentration of A divided by dt. Right? This term will give me the rate of reaction. Even this term will also give me the rate of the reaction. Agreed? Now what I'll be doing? Let me talk about this particular statement now. I'm getting minus d of A divided by dt. Minus d of A divided by dt is equal to K and concentration of A raised power 0. Right? So I can write d of A, change in the concentration of A, is equal to minus K times dt, because concentration of A raised power 0, that's going to be 1. Now, dear students, I'm going to make the integrated rate equation. I'm going to make an equation for zero order reaction, which I call as integrated rate equation. And that particular equation will be valid for all the zero order reactions. And you'll see its application part as well in some time. Just understand. So first of all, I'm going to make an integrated rate equation. So what I'll be doing, I'll be integrating on both the sides. Here I'm integrating with respect to the concentration of A. Right? I'm integrating with respect to the concentration of A. And concentration of A is changing from A0 to AT. So lower limit is A0, upper limit is AT. And here I'm integrating with respect to time, which is from 0 to t. So here lower limit is 0, upper limit is t. You can check also whether the limits are correct or not. My dear students, we know at time t is equal to 0, the concentration of reactant is A0. Right? At time t, the concentration of reactant will be AT. Perfect. Now, try to understand a few more things. My dear students, integral of dx is x. Integral of dy is y. So integral of dA will be A. Integral of dA will be A. And the limits are A0 till AT is equal to minus k will come out. Integral of dt is t. So it will come out to be minus kt. Okay. Now we use the upper limit and lower limit. It has to be AT minus A0 is equal to minus kt. So from this particular expression, you got to know AT is equal to A0 minus kt. This particular equation which I made over here, this particular equation is something which you call as integrated rate equation. This is something which you call as integrated rate equation for zero order reactions. Right? It is something which you call as integrated rate equation. For which kind of reactions? For zero order reactions. Now, my dear students, what these terminologies are? AT is the concentration of reactant left at time t. A0 is the initial concentration of reactant. T is the time in which the concentration of reactant is changing from A0 to AT. Right? Now, where all do we use this particular result? My dear students, you'll be getting a question, for example. You'll be getting a question. You'll be given with a zero order reaction in which you have to check in what time duration the concentration of reactant changes from 8 molar to 3 molar, for example. In what time duration the concentration of reactant changes from 5 molar to 3 molar, for example. How do we calculate that? With the help of this particular result, with the help of this particular expression. You'll see its application part in some time. First, I want all of you to remember this result from now onwards. AT is equal to A0 minus KT. And this particular result I am calling as integrated rate equation for the zero order reactions. Okay? Where can we use the integrated rate equation? I'll let you know in some time. When we do the questions, there you get the idea where do exactly we use it. Okay? So this was the first point which was related to zero order reactions. Point number 1. Point number 2, my dear students. Point number 2 for the zero order reactions. What is that? That's half-life. Half-life, which is represented by either T 50% or T1 by 2. Half-life of the zero order reaction. First of all, how do we define the half-life? My dear students, half-life is defined as the time taken to complete 50% of the reaction. Time taken to complete 50% of the reaction. Or in other words, you can define it like this. The time taken to reduce the concentration of reactant from A naught to A naught by 2. Let's get to know what exactly it means. Let me make you understand what it means, and then we'll be making its expression and its application as well. Imagine that you have got the reaction A gives B. Imagine that it's a zero order reaction. Let's say at time t is equal to 0, the concentration of reactant is 4 molar. Let's assume that at time t is equal to 0, the concentration of reactant is 4 molar. Now, my dear students, when the reaction will start, what will happen to the concentration of reactant? Concentration of reactant will keep on decreasing with time. Can I say there will be a time when the concentration of reactant will reach 2 molar? The time taken to complete 50% of the reaction. The time taken to complete 50% of the reaction. The time taken for the concentration of reactant to be equal to half of its initial value. That time taken is something which we call as half-life. Let's assume that in 10 seconds, the concentration of reactant is changing from 4 molar to 2 molar. That means the half-life of the reaction will be 10 seconds. As simple as that. So in short, the time taken to complete 50% of the reaction. What is meant by 50% completion? 50% completion means 50% of the reactant has got dissociated into products. 50% of the reactant has got converted into products. Right? So if 50% of reactant is converted, I'll be left with 50% of reactant as well. Okay? So I hope you just got the idea of what this half-life exactly is all about. Now people, let's try to make its general result. That is important. Have a look. Imagine you have got the reaction A gives B. Its rate constant is K and it is a zero order reaction, for example. At time t is equal to 0, the concentration of reactant is A naught. This will be 0, right? Now, my dear students, imagine that 50% of reactant is complete. If 50% of reactant is complete, that means 50% reactant has got converted into products. If 50% reactant has got converted into products, that means 50% of reactant will be still left in the container, right? So 50% of reactant means A naught by 2. This is the concentration of reactant left in the container. At time, how much? At time, T is equal to T half. Okay? At T is equal to T half, the concentration of reactant left will be A naught by 2. That means 50% of reaction has got completed. 50% reactant has got converted into product. Now, dear students, this is the concentration of reactant left. And the concentration of reactant left is represented by AT. The concentration of reactant left at time t, that is represented by AT. Now try to understand. Over here we got a condition. The condition is at t is equal to t half. At t is equal to t half, the concentration of reactant left, that is A naught by 2. At t is equal to t half, AT will be equal to A naught by 2. Now, my dear students, what is our integrated rate equation for the zero order kinetics? Integrated equation is like this. AT is equal to A naught minus KT. So what I'll be doing, I'll be using this particular condition in this particular expression, right? As per this condition, AT value is nothing, that is A naught divided by 2 is equal. This is A naught minus K. Instead of T, you'll be writing T half, correct? So from this particular equation, you got T half is equal to A naught divided by 2K. So this is the general expression which you guys are going to remember from now onwards to calculate the half-life of a zero order reaction. A general expression to calculate what? To calculate half-life of a zero order reaction. Okay, perfect. So half-life of the reaction, half-life of the zero order reaction, it's equal to A naught divided by 2K. This was the second parameter related to the zero order reactions. Okay. My dear students, the third parameter. The third parameter which is related to zero order reaction. That's what we call as completion time. Completion time, which is represented by T 100%. What is meant by completion time? Completion time is defined as the time taken to complete 100% of the reaction, in short. Okay? Time taken to complete 100% of the reaction. Okay? Try to understand what it means. For example, again you have got a zero order reaction whose rate constant is K and order of reaction is 0. Initially, for example, the concentration of reactant was A0, this is 0. Now, when the reaction will start, the concentration of reactant will keep on decreasing. It will keep on decreasing. My dear students, at time t is equal to T 100%, what will happen? I would say 100% of reactant would have got converted into product. If 100% reactant would have got converted into product, I would say the concentration of reactant left in the container at T is equal to T 100%, that is going to be 0. And concentration of reactant left in the container, that is represented by AT. So over here, I got one more condition. At time T is equal to T 100%, AT value is equal to 0. Now use this particular condition in the integrated rate equation. What is the integrated rate equation? AT is equal to A0 minus KT. Now, my dear students, AT value is 0 basically, is equal to A0 minus K. Instead of T, you are going to write T 100%. So from this particular expression, can't we calculate T 100%? So I would say T 100% is nothing, that is A0 divided by K. What is this particular result? It is the result which is going to let you know the time taken to complete 100% of the zero order reaction. This is the time taken to complete 100% of the zero order reaction. Now people, already we calculated T 50% also. Half-life of the reaction. That was equal to A0 divided by 2K. A0 divided by 2K. This was the half-life. So if you look at these two equations, if I divide these two equations, what do I get? I'll be getting T 100% divided by T 50% will come out to be 2. Right? So from this particular expression, you can say T 100% is equal to 2 times T 50%. Now, what does it mean? What does this particular expression mean? It means that a zero order reaction. Is completed. Completed means 100% completed. A zero order reaction is completed in how many half-lives? In 2 half-lives. A zero order reaction is completed in 2 half-lives, right? Perfect. For example, you have got a reaction whose half-life is 10 minutes. I'm asking you, how much time does it take to complete 100% of the reaction? Directly 2 times half-life. So 2 into 10, that comes out to be 20 minutes. So it will take 20 minutes for the reaction to get 100% completed, right? So this is one more statement which you need to know. A zero order reaction, it's 100% completed in how many half-lives? In 2 half-lives. This was the second point. Sorry, this was the third point. Now talking about the fourth point. Fourth point will be degree of dissociation. Degree of dissociation, which is represented by alpha for a zero order reaction. I hope you exactly remember how do we calculate degree of dissociation. Do you remember that? Alpha, degree of dissociation, is equal to number of moles of reactants dissociated divided by initial moles of reactants taken. Correct? Number of moles of reactants dissociated divided by initial moles of reactants taken. Now guys, try to understand. For example, you have got a zero order reaction like this. A gives B, whose rate constant is K, and order of reaction is 0. It's a zero order reaction. Imagine that at time T is equal to 0, the concentration or the moles of reactant are A0. Moles of reactant or concentration of reactant at time T is equal to 0. For example, that's A0. So this has to be 0. Correct? At time T, At time t, the concentration, the moles of reactant left, the concentration of reactant left or the moles of reactant left, that is AT, right? That's AT. Initially, the moles of reactant were A naught. At time t, the moles of reactant left are AT. Now, I want to calculate alpha value, degree of dissociation for this particular zero order reaction. Number of moles of reactants dissociated. Number of moles of reactants that got converted into products. What is that going to be? Initially, I start with A naught moles. I'm left with 80 moles of reactant. So how many moles of reactant got converted? Initially, I took A naught. Now I'm left with 80. So 80 A naught minus 80. These are the moles of reactant. This is the concentration of reactant. These are the moles of reactant. This is the concentration of reactant, which got converted into products, which got dissociated, divided by initial moles of reactants. Initial moles of reactants were nothing. That was A naught. Correct? Now, my dear students, get the value of alpha. Alpha has to be equal to A naught minus. What is AT for a zero order reaction? For a zero order reaction, AT is nothing. That's A naught minus KT. Divided by what? Divided by A naught. So A naught gets cancelled. So alpha value has to be equal to KT divided by A naught. This is how you calculate degree of dissociation for a zero order reaction which has got the stoichiometry 1:1. Right? So you're going to remember this particular parameter as well. This is the fourth parameter related to zero order reactions. That is degree of dissociation. Right? That is degree of dissociation. Alpha is equal to KT divided by A naught. A is the rate constant, T is the time, A naught is the initial concentration. Perfect. This was the fourth parameter. Talking about the fifth parameter for the zero order reactions. What is that? That is units of rate constant. Units of rate constant for a zero order reaction. My dear students, generally the units of rate constant are written as moles, liter inverse, raised power 1 minus n, and time, for example, is in seconds, second inverse. Or you can write it like this. For example, pressure is in atm, so atm raised power 1 minus n. Let's assume time is in seconds, second inverse, right? Now you are given the zero order reaction, that means n value is equal to 0. If n is equal to 0, that means I'm talking about what? I'm talking about the zero order reaction. If n is equal to 0, the value of rate constant, the unit of rate constant has to be n value 0. So it's going to be moles, liter inverse, second inverse, or choose this one, n is 0, so it's going to be atm second inverse. Perfect. So these are the units of what? These are the units of rate constant for a zero order reaction. Okay? For a zero order reaction. Now, dear students, the sixth point. The sixth point for a zero order reaction. Do remember it. I'm going to make a table over here. I'm just going to make a table over here. Over here, I'm writing time. Over here, I'm writing time. And here, I'm writing concentration of reactant. Concentration of reactant. Now, try to understand what exactly I'm going to say. Let's assume at time t1, the concentration of reactant was A1. At time t2, the concentration of reactant is A2. At time t3, the concentration of reactant is A3. At time t4, the concentration of reactant left, that was A4. Right? Concentration of reactant initially is A1. Concentration of reactant left at time t2, that's A2. Concentration of reactant left at time t3. Concentration of reactant left at time t4. Correct? Now, my dear students, I'm going to talk about the zero order reaction. Let's say the reaction is like this. A gives B. Whose table I have given you. A gives B. Whose table I have given you. For the same time interval, what does it mean? For the same time interval. What does that mean? That means T2 minus T1 is equal to T3 minus T2, which is equal to T4 minus T3. So basically, I'm considering the time intervals to be same. The time interval from here to here is equal to, from here to here is equal to, from here to here. So I'm considering the same time interval. If in the same time interval, A2 minus E1 will be equal to A3 minus A2, which will be equal to A4 minus A3. So basically, I'm trying to say, if in the same time interval, the concentration of the reactants will have the same common difference. Will have the same common difference. Do remember at that point of the time, the nature of the reaction, the order of the reaction is going to be 0. Do remember at that point of the time, the order of the reaction is going to be 0. Okay? If in the same time interval, the concentration of reactants or pressure of reactants, for example, or in general, you can say amounts of reactants, if they have got the same common difference, if A2 minus A1 is equal to A3 minus A2 is equal to A3 minus A4 minus A3, then do remember the nature of the reaction, the order of the reaction is going to be 0. It is particular condition valid for a 0 order reaction. Okay? It is a particular condition valid for a 0 order reaction. So you can directly say, after looking at the table, you can say the order of the reaction is absolutely going to be how much? It's going to be 0. Okay? Perfect. Right, guys? Now try to understand one more thing. This was the 6th parameter which you have to remember related to the 0 order reactions. 7th parameter which I want you guys to remember related to the 0 order reaction. What is that? Have a look. For example, you have got the reaction like this. A gives B. You have got the reaction like this. A gives B, whose rate constant is K, and the order of the reaction is 0. It is a 0 order reaction. Let's assume at time T is equal to 0, the concentration of reactant is A0. At time T1, the concentration of reactant is AT1. At time T2, the concentration of reactant is AT2. The concentration of reactant is AT2. Right? My dear students, if I ask you, how much time does it take? If I ask you how much time does it take for the concentration of reactant to reduce from AT1 to AT2? I'm asking you how much time does it take for the concentration of reactant to reduce from AT1 to AT2. That means what am I asking you? I'm asking you this time interval from here to here. I'm asking you this time interval from here to here. Which time interval I'm asking you? I'm asking you the time interval T2 minus T1. This is the time interval I'm asking you. How much time does it take for the reactant concentration to reduce from AT1 to AT2? So which time interval I'm asking you? I'm asking you this time interval. T2 minus T1 time interval. Right? Or let's try to write it like this. Just a second. Let's try to write it like this. Have a look. What is my integrated equation? That is AT is equal to A0 minus KT. AT is equal to A0 minus KT. This is my first condition. The first condition says at time T1, the concentration of reactant left is AT1. Now use the first condition here. So instead of AT, I'll be writing AT1 is equal to A0 minus K. Instead of T, you are going to write T1. Now use the second condition. Use the second condition in the same expression. It's going to be AT2 is equal to A0 minus K, K times T2. Correct? My dear students, this is, let's call this as equation 1, let's call this as equation 2. If I take the difference of the two, take the difference of the two, I'm going to write the final result. Let's take the difference of the two, subtract them and get the final result. Final result is going to be AT2 is equal to AT1 minus K times T2 minus T1. When do we use this particular expression? When do we use this particular expression? My dear students, in case of 0 order reactions, if they ask you how much time does it take for the concentration of reactant to reduce from AT1 to AT2, how much time does it take for the concentration of reactant to reduce from AT1 to AT2? That means they are asking you this time interval, T2 minus T1 time interval. T2 minus T1 time interval. This is the expression which you guys are going to use. This is the expression which you guys are going to use. Right? Remember this particular expression as well. I'll show its application in some time. Just wait for it. Just wait for the things. So this was the 7th parameter related to what? Related to 0 order. Let's exactly first of all have a look what all parameters we discussed about the 0 order. About the 0 order, we started with the integrated equation, right? Second, we discussed the half-life. Third, we discussed completion time. Next, we discussed degree of dissociation. Next, we discussed units of rate constant. Next, we discussed about this shortcut table method. Next, we discussed how much time does it take for the concentration of reactant to change from AT1 to AT2. This one more expression, okay? Now, the 8th parameter related to 0 order. What is that? That is graphs related to 0 order reaction. Now, you must be thinking, what are the graphs which are related to 0 order reactions? Let's try to make all the graphs which are related to zero order reaction, which can be asked. Okay, try to understand. The first graph which I'm going to make, that's going to be rate of reaction versus concentration of reactant. This is the first graph which we'll make. The second graph which we are going to make, that's going to be concentration of reactant left versus time taken, AT versus T. The third graph which I'm going to make, that's going to be half-life, A half versus A naught, initial concentration. The next graph which we are going to make, that's going to be A 100% versus A naught. Okay. The next graph which we'll make, that has to be between what? Alpha, degree of dissociation versus A naught. Okay, these are few graphs which we are going to make over here. Try to understand. The first graph is rate versus concentration of reactant. In case of zero order reactions, we know R is equal to K, concentration of A raised power 0 as per rate law. So R is equal to K. So is the rate dependent on the dependent on the concentration of reactant? Rate is not dependent on the concentration of reactant. So what has to be the nature of the curve? On changing the concentration of reactant, nothing happens to the rate. So it is independent, right? This particular graph, it is only valid for zero order reactions. Okay, point number one. Point number two. AT versus T. You already know the equation. AT is equal to A naught minus KT, correct? Now AT you are plotting along y-axis, time you are plotting along x-axis. So this will be your M, the sign here is minus, and this term will be C. So y is equal to minus mx plus C. Y is equal to minus mx plus C. The nature of the curve has to be like this. Okay, it's a straight line. If I ask you what about the slope of this particular curve? Slope of this particular curve basically is minus K. If you ask me what is the intercept, what about the intercept? Intercept is C, which is basically A naught, right? So this is the graph which is particularly valid for zero order reactions. Okay. Now people at the same time, look at this particular graph. T half versus A naught. What is the result between T half and A naught for the zero order? You know T half is equal to A naught divided by 2K, or you can say 1 by 2K multiplied by what? Multiplied by A naught. This is the half-life expression. Now T half you are plotting along y-axis, A naught you are plotting along x-axis. So this whole term has to be your M. So y is equal to mx. Y is equal to mx means straight line passing through origin. If you ask me what about the slope of this particular curve, slope is basically M, and M value is nothing, it is 1 upon 2K. Correct? 1 upon 2K. Right, people? Now at the same time, T 100% versus A naught. It will be again a straight line, but its slope is going to be what? Its slope is not going to be 1 upon 2K, it's going to be 1 upon K this time. Because you know T 100% is equal to A naught by K. T 100% is equal to A naught by K, right? Right, people? Perfect. Okay, look at the next one. Look at the next one. Alpha versus A naught. Few minutes back only we derived alpha. Alpha was equal to A naught divided by KT, I guess. Was this the expression? No, it was KT by A naught. Right? Alpha was KT divided by, yes, KT divided by A naught. So I'm asking you to make a graph between alpha and A naught. Alpha and A naught, they're inversely proportional, and whenever you have to make a curve between two variables which are inversely proportional to each other, the nature of the curve has to be rectangular hyperbola. So this is the nature of the curve. So these are the different graphs which can be asked related to what? Related to zero order reactions. I hope this is clear. Let me know quickly in the chats if all these graphs are clear. These are the different types of graphs which can be asked in case of zero order reactions. Quickly, let me know in the chats if all the things are absolutely clear to you. Right, people? Now, how do we and where do we use the expressions which I gave you in case of zero order reactions? Before that, there is the 9th parameter which I want you guys to remember. Take the screenshot of this. Take the screenshot of this. Examples of the zero order reaction. It can be the memory-based question. It can be the memory-based question. Photochemical reaction between H2Cl2. It is the direct example of zero order. Decomposition of HI over gold surface. Zero order. Decomposition of NH3 over molybdenum. It's again zero order. So these are the examples of the zero order reactions. Do remember them. Do remember them directly. Do remember them directly. So what is the special feature about these reactions? These are the zero order reactions. That means if you change the concentration of reactants, nothing is going to happen to the rate of these reactions. Nothing is going to happen to the rate of these reactions. So take the screenshot of this particular slide. This is important. Okay. Now, let's try to see exactly the equations which I gave you, the concepts which I told you related to zero order. How do we use them and where do we use them exactly? Look at the first one. Look at the first one, guys. The first question. I'll show you how to solve the equations by general approach. There are shortcuts as well, which I'll tell you later on. But right now, I'll teach you first of all how to solve the equations with the help of general approach. For a zero order reaction, A gives B. So we are given with a zero order reaction, that's A gives B. For a zero order reaction, A gives B. It was observed that at the end of an hour, 75% of A has reacted. What time? 10% A will be unreacted. Understand? It's mentioned that at time t is equal to 0. At time t is equal to 0, the initial concentration of reactant is taken as A naught. This has to be 0, absolutely. Right? This has to be 0. Okay, guys, this has to be 0. Now, it is mentioned that it was observed at the end of an hour. So, at the end of an hour, 75% of A has reacted. Now, people, if 75% of reactant has reacted, does that mean 25% of reactant will be still left in the container? Absolutely. 25% of reactant. 25% of A naught will be equal to 25 by 100 into A naught, that will be A naught by 4. So this is the concentration of reactant left in the container at T is equal to 1 hour. It is mentioned in the equation. At the end of an hour, 75% reactant has reacted. If 75% of the reactant has reacted, that means 25% of the reactant is still left in the container. Right? 25% of the reactant. That means 25% of A naught, which is going to be 25 by 100 into A naught. Do remember, AT is always the concentration of reactant left. AT always represents the concentration of reactant left. Now, what are we supposed to calculate? At what time A will be 10% unreacted? So, at what time A will be 10% unreacted? Unreacted concentration of A we have to calculate at time t. Sorry. We have to calculate at what time? At what time A will be 10% unreacted? 10% unreacted means 10% of the reactant has to be left. 10% of reactant means 10 by 100 into A naught, which has to be A naught by 10. Now, this is the value of AT. So, see how many conditions we have. Try to understand how many conditions we got. We got 2 conditions. The first condition says at T is equal to 1 hour, the concentration of reactant left is A naught by 4. The second condition, at what time the concentration of reactant left will be A naught by 10. At what time the concentration of reactant left will be A naught by 10. These are the 2 conditions. My dear students, remember, from the given conditions, from the first condition, I will be always getting the value of rate constant. From the first condition, I'll be getting the value of rate constant. From the second condition, I'll be getting the value of time. Right? And how exactly you're going to solve it from here. See. What is the integrated rate equation for the zero order kinetics? For the zero order kinetics, you know, AT is equal to A naught minus KT. This is your integrated rate equation. Correct? Now use the first condition in this integrated rate equation. AT value is nothing, that is A naught by 4. As per first condition is equal to A naught minus K. T value is equal to 1 hour. Right? So I would say K will be equal to 3 divided by 4 A naught. K will be equal to 3 by 4 A naught. What are the units of K? Well, time is given in what? Time is given in hours, right? Time is given in hours. So K units has to be moles, liter inverse, R inverse. Okay, so you got the rate constant. I told you from the first condition, we'll be getting the rate constant. Now second condition. Put the second condition in the integrated rate equation. As per second condition, AT is nothing, that is A naught divided by 10 is equal to A naught minus K value already we got, that is 3 divided by 4 A naught multiplied by T we have to calculate. So A naught cancel. So you can calculate T from here. T value will come out to be 1.2 hours. So this is something which I was supposed to calculate. At what time A will be 10% unreacted? Or you can say at what time 90% of the reaction has completed. So you got to know after 1.2 hours, you can say 10% of reactant will be left in the container, or you can say at 1.2 hours, you will find out that 90% of the reaction has got completed. Is this clear? Is this clear, guys? This was the first question which you did. Very simple question this was. Moving on to one more. I'm not using any shortcut right now. No shortcut. I'm using the general procedure of solving the equations. A zero order reaction, you're given, for example, with a zero order reaction, A gives B, whose rate constant is, for example, K, and the order of the reaction is mentioned in the equation, that's 0. Now, firstly, at time t is equal to 0, the initial concentration of reactant is A naught. This is 0, correct? Now, my dear students, it's mentioned that a zero order reaction is 20% completed in 10 minutes. A zero order reaction is 20% completed in 10 minutes. Now, what does it mean? It means that 20% of reactant has got converted into product. If 20% reactant has got converted into product, can I say 80% of reactant will be still left in the container? 80% of the reactant will be still left in the container at 10 minutes. 80% of reactant means 80 divided by 100 into A naught, right? Which comes out to be 0.8 A naught. So this is the concentration of reactant which is left in the container at 10 minutes. Okay. Now what are we supposed to calculate? At what time it will be 10% completed? Sorry, at what time it will be 80% completed? At what time the reaction will be 80% completed? 80% completed means 80% of reactant has got converted into product. That means 20% of reactant is left. So at time t, 20% of reactant will be left in the container. So 20% of A naught, 20 by 100 into A naught, which comes out to be 0.2 A naught. So this is the concentration of reactant left at time t. So how many conditions I got? Tell me. This is the first condition and this is the second condition. What am I supposed to calculate? I'm supposed to calculate t. At what time the concentration of reactant left will be 0.2 A naught. Now, my dear students, as I told you already, from the first condition, I'll be always getting the value of rate constant. From the second condition, I'll be getting the value of time, right? Now, what exactly we'll be doing? We will be using the integrated rate equation. What is the integrated rate equation for the zero order kinetics? You know it. AT is equal to A naught minus KT. AT is equal to A naught minus KT. Now, tell me one thing. From the first condition, AT value is how much? In the first condition, AT value is 0.8 A naught is equal to A naught minus K. T value in the first condition is 10 minutes. So from here, you can get the value of K. K will be 0.2 A naught divided by 10. What are going to be the units of K? It's going to be moles, liter inverse, time is in minutes. So it's going to be minute inverse, right? So K value you got with the help of the first condition. Now use the second condition in the integrated rate equation. Use the second condition. Second condition says AT is equal to 0.2 A naught is equal to A naught I'm writing as such minus K value is 0.2 A naught divided by 10 multiplied by T we have to calculate. So A naught cancel. You got one equation and from here T value will come out to be 40 minutes. So what is this T exactly? This T is the time. This T is the time which tells you that 80% of the reaction is getting completed in 40 minutes, right? You got to know 80% of the reaction is getting completed in 40 minutes. T is the time at which 80% of the reaction has got completed. T is the time at which 20% of the reactant is still left in the container as such. I hope you can easily solve these sort of questions from now onwards, right? Let's try to see a few more questions based on the zero order kinetics. My dear students, look at this particular question. Look at this particular question. We are given with a table. It's a table basically, right? And the reaction that's given to us, that's A gives B. This is the reaction that's given to me. We are given with a table. When the concentration of reactant is 1 molar at time t is equal to 0, this at this, this at this. What are we supposed to calculate? Calculate the rate constant. Calculate the rate constant. Try to understand what exactly I'm going to say. We are supposed to calculate the rate constant of this zero order reaction. K value you have to calculate. How do we get the value of K? What do you think? Dear students, try to understand. At time t is equal to 0, the concentration of reactant is 1 molar. And time t is equal to 0, the concentration of reactant we represent with A naught. So A naught value is 1 molar. It is given to me as per the equation. Right? It's given to me as per the equation. Now, the concentration of reactant left is 0 molar. When? At 120 seconds. Now you understand when the concentration of reactant left will be 0 molar. Concentration of reactant left is equal to 0 molar. What does that mean? That means 100% reaction has got completed. Right? When 100% reaction gets completed, at that point itself, you can say the concentration of reactant left is 0, right? So can I say this is the time at which the concentration of reactant left is 0? So should I be calling this time as the completion time? Absolutely, it's going to be the completion time, right? So completion time, T 100%, is given to me as the equation. That's 120 seconds. Correct? We are almost done. Do you remember the expression which I told you to, by means of which we can calculate T 100%? T 100% for a zero order reaction, that's A naught by K. So A naught by K is nothing, it is 120 seconds. So K value has to be equal to A naught divided by 120. A naught is 1 molar divided by 120. Units are supposed to be moles, liter inverse, second inverse. This is the rate constant which you were supposed to calculate. That's all. Yes? You should be able to solve these sort of questions as well. Yeah? You should be able to solve these sort of questions as well. All right. Look at this particular question. Can you give it a try? Can you give it a try quickly? T half for the zero order reaction is 1 hour. Okay, T half is 1 hour. Perfect. When the initial concentration of reactant was 2 molar. When the initial concentration of reactant was 2 molar, T half is equal to how much? T half is 1 hour. How much time does it take for the concentration to reduce from 0.5 molar to 0.25 molar? My dear students, I gave you one equation a few minutes back. And what was that equation? Try to understand. See, you are given with the reaction A gives B, whose rate constant is K. It is a zero order reaction. It is absolutely a zero order reaction as per the equation. Now, initially at time T is equal to 0, the concentration of reactant which I represent with A naught, that's given to me as, when the initial concentration was 2 molar, that's given to me as 2 molar, right? How much time does it take for the concentration to reduce from 0.5 molar to 0.25 molar? Let's assume at time T1, the concentration of reactant left was 0.5 molar. And let's assume at time T2, the concentration of reactant left was, imagine 0.25 molar, right? As per the equation, what do we have to check? We need to check how much time does it take for the concentration of reactant to reduce from 0.5 molar to 0.25 molar. So what time interval do I need to calculate? I have to calculate this time interval, T2 minus T1. Have I told you how to calculate this time interval? I gave you one direct result, if you remember, for the zero order reactions. You know, AT2 is equal to AT1 minus K times T2 minus T naught. This is the result which we derived a few minutes back only. So AT2 is given to me as the equation 0.25. AT1 is nothing, that's 0.5 minus K into T2 minus T1. Now, K value is not given to us. K value is not given to us. How do we get the value of K? My dear students, as per the equation, half-life for the zero order reaction is given as 1 hour. Half-life for the zero order reaction is given to me as 1 hour. And you know, half-life for the zero order reaction, that's nothing, that's A naught divided by 2K. So basically, A naught divided by 2K is 1, right? So from here, K will be equal to A naught by 2, right? A naught is 2, A naught is 2, and 2 by 2, that comes out to be 1. So K has to be 1 mole liter inverse. Time is given in hours. It's R inverse, right? So this is the value of rate constant. Now we got the rate constant as well. So the final expression, K value you got, K value is 1. So T2 minus T1. T2 minus T1 from here comes out to be how much? 0.2 hours, 0.25 hours. So what it means exactly? It means it will take 0.25 hours to reduce the concentration of reactant from 0.5 molar to 0.25 molar. I hope this is clear, right? I hope this is clear. Perfect. Now guys, try to understand one more thing. Look at this particular equation. Here you can do a mistake. Here you can do a mistake. Why is that? Whatever expressions I gave you related to zero order reactions, those expressions were valid for the reaction A gives B, in which the stoichiometry was 1:1. Whatever expressions I gave you till now, those are valid for the zero order reactions in which the stoichiometric coefficient of reactant was 1. But here in this reaction, stoichiometric coefficient of reactant is 2. Stoichiometric coefficient of reactant is 2. What I'll be doing here? Whenever the stoichiometric coefficient of reactant is not 1, it is anything apart from 1. At that point of time, there is something very simple which you need to do. What is that? Just try to understand. Just a second. Say, 2 times A gives P. This is basically the reaction that's given to me, right? Well, half-life of the reaction is given to me as 120 seconds. Initial concentration of reactant was given to me as 2 molar. What do we need to calculate? We need to calculate rate constant of the reaction. Rate constant of the reaction. My dear students, stoichiometry of the reactant is not 1, it's 2, right? So, what I'll be doing? T half is equal to 120 seconds. What was the formula to calculate T half for zero order? It used to be A naught divided by 2K. But this was the formula when the stoichiometric coefficient of reactant was 1. And the stoichiometric coefficient of reactant is not 1. So instead of rate constant of reaction, you'll be writing rate constant of disappearance of A. You will be writing rate constant of disappearance of A. So the formula changes here. It's not A naught by 2K reaction. It's A naught by 2KA, right? Because the stoichiometry here is 2. Okay? So this value is equal to 120, right? Now A naught value is 2. A naught value is 2. 2 got cancelled. So Ka value got equaled 1 upon 120, and its units are going to be moles, liter inverse, second inverse. But as per the question, am I supposed to calculate the rate constant of disappearance of A? No, I'm not supposed to calculate the rate constant of disappearance of A. What do I need to calculate? I need to calculate rate constant of the reaction. Do you remember I told you a few minutes back only? Rate constant of disappearance of A. It will be equal to rate constant of the reaction multiplied by stoichiometric coefficient of, right? So it's going to be Ka divided by stoichiometric coefficient of A, that is 2. It has to be equal to rate constant of the reaction. So I must say rate constant of the reaction is equal to Ka by 2. So Ka by 2 comes out to be Ka divided by 2. The value will be 1 upon 240 moles, liter inverse, second inverse. This is the rate constant of the reaction. I hope you can easily solve it from now onwards, right? So got to know where to use this particular concept? When the stoichiometry of the reactant is anything apart from 1. Yeah? Perfect, guys? All clear? No, Madhavan, that's not the half-life. Half-life is initial concentration A naught to A naught by 2. Okay? 0.5 was not the initial concentration. That was the concentration in the middle somewhere. Right? Anish, how does that matter? How does that matter? I'm changing the stoichiometry, right? I'm changing the stoichiometry. When you change the stoichiometry, basically, integrate rate constant, integrate rate equation, that automatically changes. Correct? That will change. Okay, guys. So this was all about your zero order reactions. Now first order reactions, their characteristic features, Arrhenius equation, and collision theory. That will be done in the next session, right? So is everything clear till here? Is everything clear till here? Let me know in the chats. Whatever I taught you today, is every single thing clear? Sure? So exactly assume that whatever I've told you today, whatever I've taught you today, starting from law of mass section, then we talked about the rate law, we talked about types of reactions, elementary complex reactions, we talked about molecularity, we talked about order, right? We did few questions based on experimental determination of order. We did few questions on general order, right? Then we started with the zero order reactions. We talked about certain important features which can be asked from the zero order reaction, starting with integrated rate equation, half-life, completion time, degree of dissociation, units of rate constant, all the graphs which are involved here, right? Examples, and the few questions which can be asked from the zero order kinetics as well. Okay, so I hope all the things are absolutely clear. So in the next session, which is going to be lecture number 3 of chemical kinetics, what all things we are going to cover? We'll be talking about the first order reactions, number 1. We'll be talking about the parallel first order reactions. We'll be talking about the gaseous first order reactions. Okay, we'll be talking about the Arrhenius equation and collision theory. So these are the topics which we shall be covering in the next session. So next session will be approximately some 4 to 5 hour session, because that has to be the last session, and it will happen on Tuesday. It will happen on Tuesday at 6 p.m. on your Unacademy NEET English channel. Okay. Perfect. Rahul, this is the complete English channel, right? There are a lot of teachers who take care of the Hindi speaking students. So I think I'm the only one who teaches in English this particular chemistry. So one has to teach in English as well, yeah? Or else Hindi mein padha sakta hu main. Okay, guys. And after this chapter, we shall be starting with either electrochemistry or, yeah, electrochemistry only we shall be starting. Perfect. So till now, which all chapters we completed? Do you remember? We completed mole concept. We completed redox reactions as well. Mole, redox. We completed states of matter, solid state, thermodynamics, chemical equilibrium, ionic equilibrium, and this is chemical kinetics going on. Chemical bonding we completed. So this is the 9th chapter which we are completing, guys. 9th chapter which we are completing. And at the same time, your HSP sir, he completed your GOC, isomerism, right? Hydrocarbons he completed. And apart from that, he completed your haloalkanes, haloarenes. And right now, he's taking care of your amines. So basically, in chemistry, we are done with 13 to 14 chapters. Now, there are not many chapters left. Okay, same goes for your physics. Same goes for your biology as well, right? So we'll try to complete syllabus as soon as possible so that we can go for the revisions, we can go for the crash courses, etc., right? And let me tell you, in the last week of this particular month, I'm not going to take class on YouTube. I'll be taking special classes in which I'll be teaching you inorganic chemistry, basically, starting with periodic properties. I'll let you know exactly when I'll be taking that session. Okay, I'll be giving you its link as well. So if you've not joined the Telegram yet, I would want you guys to join the Telegram as well so that you remain updated about all the sessions which I take here, right? Perfect. Perfect, guys. So with this, I'll be taking a leave. I'll see you guys in the next session. Yeah. Till then, you take care. God bless you all. Bye. Take care, guys. And do share the video with everyone so that everyone gets benefited out of these sessions. Because the content which you are getting here, that is the, I would say, best quality content across the YouTube. Okay. So take care, guys. God bless you all. Bye-bye.